Hello there and welcome to Science for Sleep, where curiosity settles in beside you and the universe becomes a gentle place to wander while your thoughts slowly unwind. Tonight, we're drifting into one of the most quietly fascinating mysteries hidden in the deep darkness of the cosmos. Not something loud or explosive, not something you'd notice at first glance, but a slow and steady pull woven into the very movement of galaxies, including our own. A soft but relentless tug, guiding entire clusters of stars toward a destination we can't see clearly. A place astronomers call the Great Attractor. The name alone sounds dramatic, maybe even a little theatrical, but the reality is far more subtle and somehow even more intriguing. It's a gravitational pull so vast that it influences the entire region of the observable universe we belong to, yet it stays hidden behind a thick curtain of dust and starlight. We know it's there because we can feel what it does, even though it refuses to show itself plainly. Before we begin this slow descent into the puzzle of it, I'd love to hear something from you. Where are you listening from tonight? And what time is it, where you are right now, in your little corner of the world? I always find it comforting that while these mysteries stretch across hundreds of millions of light years, we're sharing this particular moment together. You, wherever you're resting or settling down, and me, guiding you through a story that stretches far beyond anything any one of us could ever see with our own eyes. It's a peaceful thing, really, to know that while the universe pulls at galaxies, maybe this little space can pull your thoughts a bit more gently toward calm. And if you find this journey soothing or interesting in a way that helps you drift a little closer toward rest, it would mean a lot if you gave the video a like or subscribe to the channel. It's a small gesture, but it helps this quiet space reach someone else who might need a moment of stillness, or perhaps someone who likes to fall asleep while thinking about things far too large to worry about, but just mysterious enough to hold their attention in a soft, steady way. So, let's settle in. You don't have to focus too hard. You don't have to hold on to any details unless you want to. This isn't an exam. It's simply a gentle exploration of something enormous and hidden, something that affects us all without asking for permission or even announcing its presence. Just a slow pull from far away, shaping the motion of our galaxy while we go about our days, barely aware that we're part of a much larger drift. The Great Attractor is one of those cosmic features that doesn't need drama to be fascinating. Its mystery comes from how silent it is, how carefully it conceals itself behind the thickest part of our Milky Way's disk, and how it persuades scientists to look deeper even when the view is almost entirely blocked. Think of the universe as an ocean, not a poetic one, just a practical one. An enormous expanse where galaxies move not randomly, but in steady flows shaped by unseen currents. If you watch them from a great distance, you'd notice them drifting not outward in perfect symmetry, but slightly off balance, shifting collectively toward a region of space that gives little away. It's not the center of the universe. It's not a giant black hole sucking up everything around it. It's more like a gravitational low point, a place where matter gathers in such enormous amounts that entire superclusters can't help but inch toward it at remarkable speeds. What makes this even more interesting is that we're part of that motion. Our galaxy, the Milky Way, isn't just calmly spinning through empty space. It's also sliding at hundreds of kilometers per second toward this hidden gravitational region. And because everything around us is moving too, it's not easy to figure out exactly why. That's what makes the Great Attractor such a compelling mystery. It's not a single object. It's not shaped like anything we can easily imagine. It might not even be a single structure. It might be a combination of many things layered across vast distances, adding up to a pull strong enough to alter the motion of countless galaxies. We know it exists because the math insists on it, and the movements confirm it, even if the details remain fuzzy. But before we get too deep into all of that, let's slow down for a moment. Let yourself settle into the steady pace of this explanation. There's no reason to hurry. The universe certainly isn't in a rush. These movements happen over timescales so long that calling them slow would be an understatement. They're more like tectonic drifts of entire galactic families, carried along by the large-scale structure of the cosmos. And because everything is moving at once, it takes careful observation to notice that something unusual is happening. Astronomers didn't wake up one morning and instantly realize the existence of a massive gravitational anomaly. It took decades of measurements, patient analyses, and the persistent sense that something wasn't lining up the way it should. If you think about it, that's one of the calming things about astronomy. It's not frantic, it's not chaotic, it's a field built on long, steady looks at the sky. You wait for the data, you gather it piece by piece, you compare what you expect to see with what's actually there. And slowly, quietly, the universe shows you where the mysteries lie. In the case of the Great Attractor, the clues weren't flashy. They were subtle discrepancies in the motions of galaxies within our local region. These galaxies weren't just drifting away from each other because of cosmic expansion. They were also sliding sideways a bit, as if nudged by something off to the side. When scientists accounted for the normal expansion of the universe, there was still a leftover motion that needed explaining. Galaxies don't just invent new directions for no reason. Something was pulling them. And that something was not visible in any direct way because it sat in a heavily obscured region of the sky. Dust, gas, densely packed stars, all blocking the view like a thick fog. But the movement was unmistakable. Our entire cosmic neighborhood was drifting toward a region that didn't match what optical telescopes could see. If anything, that only made the mystery more tempting. As we move forward, the story will open up more and more. You'll hear about the large-scale maps of galaxy movements, the challenges of studying what lies behind the Milky Way's disk, the discovery of even larger structures beyond the Great Attractor, and how all of this fits into the hierarchy of cosmic architecture. But for now, we're just easing into it, letting the idea settle. A hidden gravitational pull guiding entire galactic groups without announcing its presence. Something enormous but not ominous. Something significant but not threatening. Just a natural part of how matter arranges itself on the grandest scales. It's a reminder that while we often think of the universe as empty space, it's actually full of invisible influences. Dark matter, gravitational flows, and vast clusters of galaxies all shaping one another's movements. Our home galaxy isn't isolated. It's part of a massive structure called the Laniakea Supercluster, a network of galaxies connected by gravity and motion. And the Great Attractor lies within that network, a kind of gravitational basin that helps define the direction our local region drifts in. Later on, we'll explore what lies beyond it, including another immense structure that seems to tug on everything even more strongly. But that's still ahead. For now, it's enough to picture yourself floating gently through space, carried not by sudden accelerations but by a quiet, steady drift that has been happening long before humans existed and will continue long after any of us are here to think about it. No urgency, no drama, just motion shaped by the mass of things we can see and the mass of things we can't. And even though the Great Attractor sits behind a thick veil of dust, the evidence of its pull reaches us with patient persistence, a reminder that the universe doesn't always reveal itself easily, but it always leaves clues for those willing to look closely. So as we continue, let your thoughts ease into the scale of the story, not as something overwhelming, but as something steady and strangely grounding, a slow drift through cosmic currents, a puzzle built from motion rather than sight, and a quiet realization that even our galaxy is part of something larger, moving along with countless others toward a destination we're only beginning to understand. When people imagine the universe, they often picture everything drifting outward evenly, like ripples spreading from a pebble tossed into a calm pond. It's a simple picture, and it's not entirely wrong. Ever since the early discoveries of cosmic expansion, we've known that galaxies are moving away from one another as space stretches. But that idea, while accurate in general, doesn't capture the full story. The reality is more intricate, more layered, and a bit less symmetrical than the picture most of us carried from old textbooks or classroom diagrams. The expansion is there, yes, but on top of it sits another kind of motion, a more subtle flow that doesn't follow the same pattern. This quieter drift is what begins to reveal the presence of something hidden, something that exerts a slow but steady gravitational influence across a huge part of the observable cosmos. To understand this drift, it helps to think of galaxies not as independent objects floating in empty space, but as parts of vast structures shaped by gravity on enormous scales. While cosmic expansion pushes everything apart, gravity pulls things together. These two influences don't cancel each other out. Instead, they overlap, creating a complicated choreography. On large enough scales, expansion wins, but on intermediate scales, gravity still has a strong voice. Galaxies cluster, form groups, create filaments, and settle into patterns shaped by matter concentrated in certain regions. These are not small clusters either. They're gigantic assemblies of galaxies stretching across hundreds of millions of light years. The pull from such enormous gatherings can affect the movement of everything nearby, even our own Milky Way. This brings us closer to the idea of the hidden drift. Astronomers long ago noticed that galaxies near us were moving in ways that didn't fit the simple pattern of expansion alone. They were not just being carried outward by the stretching of space. Many of them were also moving sideways in relation to the expected expansion flow. And when scientists examined the direction of that sideways motion, they realized that a large number of galaxies, including our own, seemed to be heading toward the same general region of the sky. It wasn't a small deviation. It was consistent across many observations. Something was nudging an enormous number of galaxies in a similar direction. This wasn't immediately obvious. You can't watch a galaxy move in real time with your eyes or with a telescope. The movements are far too slow on human timescales. Instead, astronomers measure how galaxies move by looking at the light they emit. When a galaxy is moving away, its light stretches slightly, shifting toward the red end of the spectrum. When it's moving toward us, its light compresses slightly, shifting toward the blue. This method, known as the Doppler effect, lets scientists determine not only that galaxies are receding, but also whether they have any additional motion layered on top of the expansion. When these measurements began piling up, a strange picture emerged. The Milky Way and many galaxies around us were moving toward a region of the sky near the constellations Hydra and Centaurus. Not rushing, not accelerating wildly, but gliding with steady purpose. Their motion couldn't be explained by local gravitational effects alone. The forces within our local group of galaxies, or even within nearby clusters, weren't strong enough to account for the speed and direction of the drift. Something larger was at play, something immense, far beyond anything visible in ordinary photographs of the night sky. It's important to pause here and consider what this kind of discovery means. It's not like spotting a bright object and wondering what it is, it's realizing that the entire motion of countless galaxies is out of place. That's a different kind of mystery. It's more structural, more foundational. It suggests that there is a large-scale gravitational influence working across a region of the universe so vast that individual galaxies are merely small pieces of a much larger puzzle. This drift isn't the kind you notice by pointing a telescope somewhere and seeing immediate change. It's the kind you uncover by gathering slow, steady measurements from all directions, then comparing them, then adjusting models, then recalculating, then realizing the data tells a story you didn't expect. This story begins with a concept astronomers call peculiar velocity. In everyday language, that simply means the motion of a galaxy that isn't due to cosmic expansion. If expansion pushes galaxies outward in all directions, peculiar velocity is the part of the movement that veers off from that path. It's the sideways slide, the deviation from what the universe's general stretching would predict. Peculiar velocities point to gravitational influences. If a galaxy is moving faster in one direction than expansion alone can explain, something must be pulling on it. Scientists mapped these peculiar velocities and found a pattern. The pattern was not random, it was coherent. Many galaxies were flowing in roughly the same direction. When the motion of our own Milky Way was calculated, the result aligned with the same pattern. We're part of that motion. We're participating in the drift. The universe around us isn't static. It isn't balanced. It's leaning, ever so slightly, toward a hidden gravitational basin. It's not pulling things together quickly. It's not creating sudden changes. But over millions and billions of years, its influence becomes undeniable. Once you begin to grasp the scale of this, it takes on a calming quality. These motions are slow, predictable, and steady. There's no need to imagine sudden movements or dramatic shifts. It's more like the long-term settling of vast regions of matter, shaped by gravitational influences that have been present since the early days of the universe. Galaxies drift the way glaciers move across a landscape. They don't rush, they don't leap. They slide along paths determined by enormous structures around them. Over time, these paths become clear, even if the reasons behind them take longer to uncover. The hidden drift also reminds us that our place in the universe is not centered or privileged. We're not sitting still. We're not anchored. We're part of a long, slow current. Even the sun, which feels so stable in the sky, is travelling through the Milky Way at high speed. And the Milky Way itself is moving toward this larger gravitational region as part of an even greater structure. Everything is in motion. Everything is part of a larger pattern. There's no true stillness on cosmic scales, only relative calm shaped by gravitational balances that play out over unimaginable distances. But what creates these enormous gravitational regions? The answer lies in the distribution of matter in the universe. Matter isn't scattered randomly. It's arranged in a cosmic web of filaments, clusters, and voids. The dense regions pull on everything nearby. The sparse regions contribute less. Over billions of years, matter has been drawn into these dense regions, creating gravitational wells that influence the motion of galaxies far beyond their visible boundaries. The hidden drift we're talking about is a result of one of these wells, one so massive and so distant that its full shape is not immediately visible. Part of it is blocked from our view. Part of it extends far beyond where early measurements could reach. But its influence shows up clearly in the numbers. As scientists began tracing these motions, they realized that the hidden drift wasn't caused by something small or isolated. It had to be tied to a structure much larger than typical galaxy clusters, something on the scale of a supercluster or even larger. This realization didn't solve the mystery, but it did narrow it. Whatever was causing the drift had to contain vast amounts of mass, and not just ordinary mass. Much of it would likely be dark matter, the invisible substance that makes up most of the mass in the universe. Dark matter doesn't emit light, so it wouldn't show up in telescopes, but its gravitational effects are unmistakable. All of this brings us closer to understanding why the drift points us toward the region known as the Great Attractor. The gravitational basin responsible for this motion is located in a direction that is unfortunately one of the most difficult to observe from Earth. The Milky Way's disk blocks our view with dust, gas, and stars. The area we're trying to study sits almost directly behind some of the densest regions of our own galaxy's structure, creating a natural blind spot. But cosmologists don't need to see something directly to detect its influence. The motion of galaxies speaks for it. This steady drift is not something to be concerned about. It doesn't change life on Earth. It doesn't alter our future in any immediate or dramatic way. It's simply the large-scale motion of our galaxy being shaped by structures far beyond our local neighbourhood. It's a slow journey, measured not in human history but in cosmic time. A reminder that the universe operates on scales so large and so slow-moving that the best way to appreciate them is by letting the mind settle gently into the idea, instead of trying to grasp every detail at once. As we continue through this story, you'll see how the hidden drift leads scientists toward deeper investigations. Measurements become more precise, instruments improve, datasets expand. The picture gradually becomes clearer. The drift isn't random. It's part of a vast flow called a bulk motion, a large-scale movement of galaxies that share a common path. Understanding the path helps reveal not just where we're heading, but also what lies in the direction of that motion. And gradually, the concept of the Great Attractor becomes less like a mysterious label and more like a natural conclusion to a long trail of evidence. Something enormous is affecting the motion of entire superclusters, something located in a region we can't easily observe, something that has been shaping the local structure of the universe for billions of years. Understanding the hidden drift is the first step toward uncovering what that something might be. When astronomers first started noticing something unusual in the motions of galaxies near us, it wasn't because of a sudden discovery made on a single night. It wasn't the kind of moment where someone looks through a telescope, gasps, and instantly realizes that the entire universe is behaving differently from what they expected. It was much quieter than that. The odd movement revealed itself slowly, almost reluctantly, hidden inside patterns that didn't line up with predictions. These patterns came not from glamorous photographs of star fields, but from careful measurements of how galaxies shift in their positions relative to us over long stretches of time. The shift wasn't large, it wasn't dramatic, but it didn't fit into the tidy picture astronomers had built for decades about how the universe should be moving. Before this puzzle appeared, the general expectation was that galaxies simply drift outward with the expansion of the universe. Each one moves away from every other one, and the farther away it is, the faster that outward movement becomes. This has been a core part of cosmology since the mid-20th century. But when scientists started analysing the motions of galaxies in detail, they began noticing slight deviations from the expected pattern. These deviations weren't random. They pointed toward a specific direction, and they weren't small enough to dismiss as measurement error. Something real was happening, even though no one could see the cause directly. One of the earliest hints of this came from studies conducted on the microwave background radiation, the faint glow left over from the early universe. That glow is remarkably uniform, but it has tiny variations in temperature. One of those variations creates what's called a dipole pattern. This pattern shows that Earth, the solar system, the Milky Way, and everything around us is moving relative to that ancient light, and the speed is significant, far larger than what local gravitational influences should produce. We're travelling at hundreds of kilometers per second in a particular direction. That on its own wasn't alarming, but it had consequences. It suggested that our entire region of space is part of a larger flow, shaped by influences far beyond the boundaries of our galaxy, or even our local group of galaxies. To confirm this wasn't a coincidence, scientists turned to the motions of nearby galaxies and galaxy clusters. When they calculated those motions, they found the same trend. Many of them were drifting in that same direction. They were not just expanding outward with the universe, they were sliding sideways toward a region of the sky where nothing obvious seemed to be waiting for them. The galaxies didn't seem to care what was visible there. They were reacting to something that wasn't easy to see. These initial findings brought more questions than answers. The first instinct many had was to assume the forces causing these unusual motions must be located in regions hidden by the Milky Way. The band of our galaxy covers a large part of the sky, filled with dust, dense gas clouds, and millions of stars. Light from beyond that region has a hard time reaching us. It gets scattered, absorbed, and blocked. So even though astronomers scanned the sky for bright clusters or massive structures that could cause this drift, the view remained unclear. As a result, the strange motion was discovered long before its cause could be identified. It was like feeling a strong breeze but not being able to see what's pushing the air. The effect was obvious, but the source was concealed. And that created an unusual situation. Astronomers had to map the motions of galaxies more accurately, hoping that the direction and speed of those motions would eventually point them towards something real, something measurable. Galaxies move in 3 dimensions, which means identifying the full motion of one requires detailed measurements. The more galaxies you measure, the better your understanding becomes of how entire regions of the universe behave. When these measurements were collected on a large scale, they showed a clear preference in direction. The data didn't scatter randomly. It flowed. Not like a river, not like a stream, just steadily in a shared direction, as though the galaxies were leaning towards something. This collective movement is often described as a bulk flow, and it is one of the main pieces of evidence that something in the distance is creating a gravitational pull strong enough to drag entire clusters of galaxies along with it. Bulk flows aren't mysterious in themselves. They happen naturally when enormous concentrations of mass exist. The issue here was that the mass wasn't visible. For a long time, nothing showed up in pictures or in catalogues of known structures that seemed large enough to be responsible. The region was too obscured. So, scientists had to depend on the motions themselves to reveal the nature of whatever was causing this drift. One of the key measurements involved observing the movement of galaxies in the Centaurus and Hydra regions. Their velocities indicated that they weren't simply moving away from us because of cosmic expansion. They were being pulled toward a specific location. Their motion matched the dipole pattern detected in the cosmic microwave background. And when the motion of galaxy clusters beyond them was added to the picture, the same pattern appeared again. It didn't matter whether scientists looked at relatively nearby galaxies or those much farther away. The direction remained consistent. This was too significant to ignore. Something that could influence such a large volume of space had to be extremely massive. But the sky didn't reveal it directly. What made this especially frustrating was that telescopes used at the time could easily detect large clusters of galaxies. They could spot superclusters millions of light years across. But when they looked toward the region causing the drift, they mostly saw the thick glow of our own galaxy in the way. This led to a focus on indirect observation. Instead of trying to see the structure directly, scientists studied its gravitational effects. These effects are reliable indicators of mass, even when the mass itself is invisible. Whether the mass consists of stars, gas, dark matter, or combinations of all three, gravity affects the movement of galaxies the same way. If something is pulling, galaxies move toward it. If something is extremely massive, galaxies move faster. And if galaxies continue moving in that direction even when other influences should have dominated, it means the mass must be unusually large. Gradually, astronomers began assembling the picture piece by piece. The strange motion wasn't something happening only to a few galaxies. It was happening to entire clusters. The Virgo cluster, which is relatively close to us in cosmic terms, was moving in that same general direction. The Hydra Centaurus cluster, farther away and much more massive, was also moving toward the same location, and so was the Norma cluster. When several large clusters all drift toward the same region, the explanation has to be something large enough to dominate their combined gravitational environment. As more data accumulated, scientists noticed that the motion wasn't limited to one specific scale. Smaller groups of galaxies moved in the same direction as larger ones. It was a hierarchical flow, meaning galaxies at many distances were all being influenced by the same gravitational source. This added to the conclusion that whatever was causing the drift was huge, on the order of tens of millions of light years across or more. Not a single galaxy, not even a typical cluster, something much larger. At this point, researchers began using different parts of the electromagnetic spectrum to look beyond the visible band. Radio waves can pass through dust, so can X-rays. Infrared light can cut through many of the obstacles that block visible light. By examining the same region using these wavelengths, astronomers hope to spot clusters and structures hidden behind the Milky Way's disk. These efforts did reveal a few important pieces of the puzzle. They showed that the region contains clusters of galaxies that had never been catalogued before. Some of them were quite massive, but they didn't seem large enough to fully explain the motion. The more astronomers looked, the bigger the puzzle became. The newly discovered clusters helped, but they weren't the complete answer. The speed of the drift still required more mass than had been identified. It seemed increasingly likely that the gravitational force was coming from a combination of structures, some visible, some hidden, and possibly some much farther away than expected. Another important insight came from refining how distances are measured. Galaxies don't all sit at the exact same distance from us, and knowing how far away each one is matters. Distance affects the interpretation of their motion. If a galaxy is farther than expected, its motion might look slower or faster than it really is. Improvements in distance measurements helped clarify the picture. Over time, the drift became more defined. It pointed to an area larger than originally estimated. The motion was not toward a small region, but toward a broad, extended zone of space. As these refinements accumulated, the strange motion stopped being viewed as an anomaly. It became a guidepost. It indicated where to look next. It suggested that the structure causing the drift was part of a much larger gravitational environment. And once scientists understood that, they started discovering additional structures beyond the originally identified region. Those structures helped explain why the drift is so strong and why earlier observations didn't capture the full picture. Even though much of this analysis happened gradually, one thing remained constant: the movement itself. Every time new data was added, the direction of the motion stayed the same. It was like tracing a weak current in a vast body of water. You might not know what lies ahead, but the direction of flow is undeniable. You follow it because it's the only consistent part of the puzzle. This strange motion remains one of the most compelling clues in understanding the large-scale structure of the universe. It shows how galaxies interact with the gravitational landscape around them. It confirms that dark matter must be shaping the universe in ways we don't see directly. And it demonstrates how even enormous structures can remain hidden behind familiar obstacles, waiting to be discovered through careful measurements rather than through direct observation. When astronomers finally accepted that galaxies across our region of the universe were drifting in a shared direction, the next question was why this motion appeared as strong as it did. It wasn't enough to know that the movement existed. The speed and coherence of the drift demanded an explanation that went beyond local structures. To understand it, scientists had to step back and consider how gravity shapes the universe on different scales. The forces that guide galaxies are not limited to nearby neighbours. They come from everything within reach, from massive clusters to the large-scale arrangement of matter that forms the cosmic web. And once you examine all of this together, the picture begins to resemble a tug-of-war, not between two sides but among many, each one pulling with a different strength and over a different distance. This tug-of-war doesn't happen quickly. The movements involved take place across billions of years. They are so slow that the only way to notice them is through careful measurements of light and redshift. And yet, despite the slow pace, the competition between gravitational influences is real and unavoidable. The universe is not evenly filled with matter. Some regions contain far more mass than others. Some are almost empty. These imbalances create flows of motion that stretch across enormous distances, guiding galaxies the way slopes guide rivers. If the universe were perfectly uniform, galaxies would simply drift outward evenly with the expansion. But uniformity is not what we see. Instead, the cosmos is a landscape shaped by peaks and valleys of mass, with galaxies sliding gradually toward the deeper wells. To understand how these wells influence motion, it helps to imagine that every cluster of galaxies exerts its own gravitational pull. If two clusters sit near each other, galaxies between them feel the combined influence. If one cluster is significantly more massive, its effect dominates. But even then, a galaxy rarely feels just one pull. It feels the sum of all the pulls combined. In practice, this means every galaxy is participating in a constant balancing act among many competing gravitational directions. Nearby structures tug one way, distant superclusters tug another. Sometimes these pulls almost cancel out. Other times, they reinforce each other and create a stronger flow. The movement we experience is the result of all these pushes and pulls playing out over enormous spans of time. This is what makes the strange motion we've discussed so intriguing. The pull affecting our region is not small. It's not the kind of influence a single cluster, or even a moderate supercluster, could create on its own. The tug has to be large enough to overcome other gravitational influences acting in different directions. That requires extraordinary mass, and the fact that so many galaxies share the same drift means the pull is felt across a vast area of the universe. The region we're talking about isn't just a small part of the cosmic web, it's a substantial portion of it. Many galaxies far beyond our local group feel the same directional influence, even when they sit in environments that would otherwise shape their motions differently. At first, it wasn't clear which structures were contributing most to this pull. The Hydra Centaurus region contained clusters massive enough to make a difference, but calculations suggested their combined mass still wasn't enough. Nearby clusters such as Virgo were simply too small to account for the full drift. Even when scientists included dark matter in the models, the known structures didn't provide a complete explanation. That led researchers to search farther out, to see whether more distant masses were contributing to the effect. And indeed, as larger surveys expanded the map of the universe, they revealed that gravitational influences don't fade away quickly. Even structures hundreds of millions of light years from us can exert a noticeable pull when their combined mass is large enough. This is where the tug-of-war image becomes essential. Our galaxy sits inside a complex gravitational landscape. On one side, the Virgo cluster pulls us gently. On another, the Hydra and Centaurus clusters add their influence. The Norma cluster contributes as well. Farther out, even more massive regions begin to exert their pull, and beyond those lie enormous scale structures that shape the overall flow of matter across this part of the universe. When all these influences combine, they create a net direction, and that direction becomes the shared motion we observe. It's not a simple matter of one giant object pulling everything in a straight line. It's the result of many structures, each tugging in its own direction, with one region emerging as the strongest influence in the mix. If we imagine being able to see gravitational fields directly, without interpreting light or relying on redshift, these forces would appear as a series of gradients across the universe. Not literal hills or valleys, but differences in the gravitational potential. The deeper the potential, the stronger the pull. The hidden drift we detect is simply our path through this landscape, shaped by the deeper valleys. Once we recognize this, the motion becomes easier to understand. We are not being drawn toward a single point because that point is special in some isolated way. We are being carried along by the gravitational shape of the universe around us. Galaxies don't resist this. They don't try to hold their positions or maintain independence. They follow the gravitational field because they have no choice. Motion in the universe is dictated by the distribution of matter on all scales. This includes visible matter, invisible dark matter, and the overall arrangement of density across the cosmic web. The tug-of-war becomes more intricate when you include voids, the enormous empty spaces between filaments. These voids exert an indirect influence. They don't pull on galaxies, but regions with less matter effectively allow galaxies to drift away from them more easily. When a galaxy sits near the edge of a dense region and a void, the dense region dominates the pull. The void contributes by not pulling at all. The result is a stronger net drift toward the area with more mass. The pull affecting our galaxy includes contributions from all these effects. But one region stands out as the dominant influence across our part of the cosmic web. This region lies behind the thickest part of the Milky Way and cannot be fully observed using visible light. Yet, despite being concealed, its effects reveal it. The drift toward this region is not slight. It's not subtle. It's strong enough that the Milky Way moves at hundreds of kilometers per second relative to the cosmic microwave background. For a galaxy of our size, that's significant. And when we observe other galaxies moving in parallel directions, the collective movement makes it clear that the tug-of-war has a favoured winner in this area. One of the ways scientists confirm this gravitational competition is by comparing observations with simulations. Cosmologists build models of the universe based on the laws of physics, and then populate them with billions of particles representing matter and dark matter. These simulations show how structures form over time. They also reveal how gravitational flows should behave when certain densities and masses are present. When the simulations include extremely massive structures in the region where the Great Attractor lies, the resulting flows resemble what we see in actual measurements. But when the simulations leave that region empty or underpopulated, the flows are weaker and do not match reality. This is indirect but powerful evidence. The motion we observe is consistent with a large gravitational region dominating the tug-of-war. We often think of gravity as something simple: an apple falls, a planet orbits. But on cosmic scales, gravity becomes more complex because the distances are so vast and the influences so widespread. A galaxy doesn't just respond to what's near it, it responds to everything across a broad environment. The balance of forces might tilt slightly one way or another depending on where matter is concentrated. Over millions of light years, these slight tilts become meaningful. The tug-of-war isn't sudden, it's persistent. And persistence, when combined with enormous distances, turns small influences into large-scale motions. The strange part of this story is that the forces involved are not symmetric across the sky. If you look in one direction, the density of matter is high. If you look in the opposite direction, the density is lower. This imbalance creates a net pull, and when you map the structures, the imbalance grows even stronger. The gravitational basin around the Great Attractor region doesn't stand alone. Behind it and around it lie additional concentrations of matter. These include clusters and superclusters that extend far beyond the original area, identified as the source of the drift. So although the Great Attractor is important, it's also part of a larger gravitational environment, one that extends deeper into the universe and shapes motion over even greater distances. This broader environment includes structures such as the Shapley Supercluster, which lies even farther in the same general direction. Its influence is enormous. It contains enough matter to rival or exceed many other known structures, and it contributes to the tug-of-war in a significant way. When the influence of Shapley is included in the calculations, the strength of our region's drift becomes easier to understand. The Great Attractor provides a substantial portion of the pull, but Shapley adds to it, reinforcing the direction of motion. It's like having multiple ropes all pulling from the same direction. Even if one rope is partially hidden behind an obstacle, you can still feel the combined pull of all of them. Understanding this combination of forces doesn't take away the mystery, it adds context. It shows why the motion remains so steady. It helps explain why galaxies that lie far beyond our supercluster share the same broad direction. And it illustrates how large-scale cosmic motions are rarely the result of a single isolated cause. The universe is too big and too interconnected for that. Instead, motion arises from the combined pattern of many influences acting together, forming long-range flows that guide galaxies through the cosmic web. This part of the story also helps explain why the strange motion we experience is not temporary. It's not a brief anomaly, it's part of a long-term drift that has been happening since the earliest days of structure formation. It has probably changed gradually over time as different structures formed, merged, and grew. As clusters collided or as dark matter halos expanded, the tug-of-war shifted. Our galaxy's path likely shifted with it. But the overall trend remains consistent because the gravitational environment has evolved in a way that maintains these large-scale flows. Gravitational influence is slow to change. Massive structures do not disappear. They grow larger as they attract more matter. So as time passes, the motion of galaxies through this environment continues. There's no sense in which the Great Attractor's pull will suddenly stop. There's no scenario in which galaxies abruptly veer off in new directions. The tug-of-war will continue as long as the structures exist, and even as larger structures beyond them rise in importance, the combined influence will still guide the flow. All of this makes the motion less mysterious and more natural. It's simply the cosmos behaving as gravity requires. The strange part, perhaps, is that much of the influence was hidden behind our own galaxy's disk. The dust and stars blocked our view and delayed our understanding. But the motion itself was always there, waiting to be recognized. The tug of war only becomes puzzling when we're missing pieces of the map. As those pieces fill in, the picture begins to make sense. This gradual uncovering of the forces shaping our region is part of what makes cosmology such a patient science. The answers don't arrive in sudden leaps. They arrive through persistence, through repeated measurements, and through the gradual refinement of models. The Great Attractor is a perfect example. At first it seemed like a singular anomaly. Then it became a suspected cluster. Later it became part of a supercluster, and eventually, as larger structures were discovered, it became one part of an even bigger influence. The tug-of-war we're part of is not a dramatic event. It's steady, predictable, and deeply rooted in the distribution of matter across a vast region of space. When astronomers first began piecing together the unexpected motions of galaxies in our region of the universe, they faced a strange challenge. The observation showed a clear direction of movement, a steady drift that couldn't be explained by simple expansion. But when they looked toward the region responsible for this drift, the sky offered almost no clue as to what was hiding there. Nothing stood out. Nothing visible appeared large enough or dense enough to explain the gravitational influence that the measurements demanded. It was as if the universe were tugging on our galaxy from behind a curtain no telescope could easily see through. This is where the story of discovering the invisible pull becomes a story not of what was seen, but of what couldn't be seen. It's a story built on absence, on blocked lines of sight, and on clues scattered across data sets that didn't immediately fit together. The process required careful reasoning and a willingness to trust the numbers even when images showed almost nothing in the region that mattered. It also required astronomers to look beyond the boundaries of visible light, using wavelengths better suited to cutting through the thick barrier of material within the Milky Way. The first obstacle was straightforward. Our galaxy is messy. The Milky Way stretches across the sky as a broad band filled with stars and dense clouds. The region astronomers needed to examine sites almost directly behind one of the heaviest concentrations of dust and gas. This area is often called the zone of avoidance, a region where visible light struggles to get through. Telescopes that rely on optical wavelengths see scattered patterns of bright stars and dim clouds, rather than the galaxies sitting millions of light-years beyond them. In many directions, this zone hides large sections of the universe, acting like a fog that distorts and blocks whatever lies behind it. For decades, astronomers routinely ignored this part of the sky because studying it was impractical. The obstacles were too thick, the field was too cluttered. The cost of trying to look through it outweighed the benefits. So when the unusual motions of galaxies pointed directly toward this blocked region, the challenge grew. The invisible pull was coming from an area that had long been overlooked simply because it was so difficult to observe. The process of uncovering what lay behind the Milky Way's bright band required a shift in strategy. Optical telescopes were no longer enough. Instead, astronomers began turning to wavelengths capable of penetrating dust. Infrared light, radio waves, and X-rays all became essential tools in the search. These wavelengths interact differently with dust and gas. Where visible light scatters and fades, infrared can pass through more easily. Radio waves can travel even farther, revealing structures hidden from optical view. X-rays can highlight hot gas in galaxy clusters, mapping their presence even when the galaxies themselves remain partially obscured. One of the first breakthroughs came from infrared surveys that scan the sky for the faint glow of galaxies beyond the Milky Way's thick mid-plane. Infrared detectors collected emissions from stars and warm dust within distant galaxies, revealing objects that had never been catalogued. These discoveries didn't immediately solve the mystery, but they provided early hints. The region behind the Milky Way was not empty. It contained clusters of galaxies that simply didn't show up clearly in optical surveys. These clusters could have contributed to the gravitational pull influencing our region. But even with these discoveries, the mass still didn't seem large enough. Radio observations offered another way forward. Hydrogen gas emits radio waves at specific frequencies, and these waves can travel enormous distances without being absorbed by dust. Telescopes tuned to detect hydrogen emissions began mapping the hidden galaxies behind the Milky Way. This allowed astronomers to track the movement of these galaxies, determine their distances, and include them in the larger puzzle of cosmic flow. The number of galaxies detected increased steadily. Entire clusters appeared that had been invisible in the past. Each discovery added to the understanding of the gravitational environment, even if none fully explained the drift on its own. Then came X-ray observations, which proved especially valuable. Galaxy clusters often contain extremely hot gas that emits X-rays. These emissions can reveal the presence of a cluster even when the galaxies within it remain unseen. When X-ray telescopes examined the region, they detected several clusters hidden by the Milky Way. Some of them were quite large. Their combined mass helped fill in the missing pieces of the gravitational map. But again, the picture remained incomplete. The gravitational influence seemed greater than the visible matter accounted for. And while dark matter certainly plays a major role in cosmic structure, the mass distribution still needed clearer definition. As more surveys added data, the gravitational landscape became easier to interpret. The flow of galaxies in our region pointed toward the Hydra Centaurus supercluster, a massive assembly of galaxies sitting not too far from the hidden region. This structure alone could explain part of the drift. Hydra Centaurus contains several clusters large enough to exert noticeable influence. But the speed and coherence of the drift suggested that another major source of gravity lay behind or near it, one that had not yet been fully identified. This deeper source became known as the Great Attractor, not because it had been seen, but because its gravitational influence matched what such a region would produce. The attractor here isn't an object, but a gravitational feature, an area where the combined mass of galaxies, clusters, dark matter and gas creates a low point in the gravitational potential. Galaxies flow toward it, not because they are being swallowed or captured, but because gravity guides them into regions of higher density across the cosmic web. Once astronomers accepted that this invisible region had to exist, they began refining its location by analysing the motions of many galaxies at varying distances. If closer galaxies were moving in one direction but more distant galaxies were moving with even greater speed, that indicated a larger influence farther away. If the motion changed direction across the sky, that helped narrow the position of the pull. The data gradually traced out a rough path. The Great Attractor appeared to lie near the Norma cluster, a massive cluster partially hidden but still detectable in certain wavelengths. The Norma cluster became a central part of the story. It sits in a region so obstructed by the Milky Way that optical observations barely showed anything. But X-ray and radio surveys revealed that Norma contains hundreds of galaxies bound together by an enormous concentration of dark matter. Its mass is significant enough to contribute strongly to the drift. When combined with the mass of Hydra Centaurus and surrounding regions, the influence approached what observations demanded. But even then, there was still a gap. The motion remained stronger than the known structures could explain. This led to another important realization. The invisible pull didn't come from a single structure. It came from a combination of structures, layered across tens of millions of light years. The gravitational basin was wider and deeper than originally thought. When astronomers looked beyond the region of the Great Attractor, they found even larger structures in the same general direction. Among them was the Shapley Supercluster, one of the most massive superclusters known. Shapley contains dozens of galaxy clusters, and enough mass to significantly affect the motions of galaxies over great distances. Once Shapley's influence was factored into the calculations, the numbers began to make sense. The invisible pull wasn't simply a local anomaly. It was part of a larger gravitational environment extending far beyond the initial region. the Great Attractor became one component of a broader network of structures shaping the flow of galaxies in this part of the universe. The motion of the Milky Way, the Virgo cluster, the Norma cluster, and countless others all began to align with the gravitational influence of Hydra Centaurus, Norma, and Shapley acting together. This discovery showed why the pull appeared so strong even when early observations didn't reveal much. The visible part of the gravitational basin was only a fraction of the whole. Much of the influence came from regions deeper within the cosmic web, some of which lay outside early survey boundaries. It wasn't a single giant object hidden behind dust. It was a layered set of structures, each contributing to the pull. And because the influence of gravity spreads across enormous distances, the combined effect became powerful enough to explain the drift. As the structure of the region became clearer, astronomers began mapping the full pattern of galaxy motion. The result was a flow that didn't stop at the Great Attractor. Galaxies inland of the Norma cluster continued past it in the direction of Shapley. This meant that the Great Attractor was not the ultimate destination of the drift. It was more like a stopping point along the way, a gravitational ridge that galaxies crossed as they flowed toward a deeper basin farther out. The invisible pull turned out to be deeper and broader than anyone expected. This revised understanding didn't diminish the importance of the Great Attractor. Instead, it placed it within a more complete context. The gravitational environment shaping our region includes influences from multiple superclusters, and the Great Attractor remains a central part of that environment. It acts as one of the gateways through which galaxies pass on their way toward denser regions. The process of discovering this invisible pull is a reminder of how much of the universe remains hidden from immediate view. Even now, with more advanced instruments, parts of the zone of avoidance remain difficult to study. Dust clouds continue to block optical wavelengths, but through infrared, radio, and X-ray observations, astronomers have been able to uncover much of what lies beyond, and each discovery helps refine the picture of how gravity shapes the cosmic web. What makes this story particularly compelling is that it shows how the universe reveals itself through motion rather than appearance. The galaxies acted like markers drifting across a vast landscape. Their motion traced out the gravitational shape of the universe. Through them, astronomers could map regions they couldn't see. The invisible pull wasn't discovered through direct observation. It was discovered because galaxies responded to it consistently and predictably. That consistency became a guide, and the guide eventually led to the structures responsible. When astronomers tried to understand why so many galaxies were moving in the same direction, they needed a way to separate the motion caused by the expansion of the universe from the motion caused by gravity. That distinction wasn't obvious at first. Every galaxy we observe is affected by both processes at the same time. The entire universe expands, carrying galaxies away from each other, but gravity creates deviations from that smooth expansion. These deviations are what scientists call peculiar velocities. The word peculiar doesn't mean strange in a dramatic way. It simply means the extra motion a galaxy has on top of what expansion predicts. And it's within these extra motions that the clues to the Great Attractor first began to appear. Before these measurements became central to cosmology, the idea of peculiar velocity was more of a technical detail. It wasn't considered a major tool for understanding large-scale structure. For a long time, astronomers focused mainly on the expansion of the universe and how fast objects were moving away. But once deeper surveys began mapping thousands of galaxies, patterns emerged that couldn't be ignored. Some galaxies weren't behaving according to what expansion alone would cause. They were moving faster or slower, or in slightly different directions than expected. When these differences lined up consistently, they pointed towards something significant. To calculate peculiar velocities, astronomers first need accurate distances. Without knowing how far away a galaxy really is, it's impossible to determine how much of its motion is due to expansion. For example, if a galaxy is farther away than initially thought, it should be moving away faster. If its speed doesn't match that expectation, the difference becomes its peculiar velocity. But measuring distances to galaxies is one of the most challenging tasks in astronomy. There's no single method that works for all distances. Scientists rely on a series of techniques, each valid at different ranges, from nearby galaxies to faraway ones. For nearby galaxies, astronomers can use methods like observing variable stars. Some stars change brightness in predictable ways, and their properties reveal how far away they are. For slightly more distant galaxies, scientists measure the size of certain features or use relationships between brightness and rotation speed. Each method adds a layer of understanding. As these techniques improved, distance measurements became more accurate, and peculiar velocities became easier to quantify. Once accurate distances were available, astronomers compared them to redshift, the stretching of light caused by motion. A galaxy's redshift gives a sense of how fast it's moving away because of expansion. If the galaxy's actual motion doesn't match what expansion predicts, the difference is its peculiar velocity. This process revealed galaxies that were approaching us faster than expected, drifting sideways, or moving in directions that didn't fit simple models. When enough galaxies were measured, the patterns became impossible to dismiss. In certain regions of the sky, galaxies showed large, peculiar velocities pointing toward the same general direction. This wasn't something that happened randomly. Random motion wouldn't create a coherent pattern. Instead, these deviations hinted at a large-scale gravitational influence pulling galaxies consistently in one direction. The first major clue came from measuring the motion of the local group, the small collection of galaxies that includes the Milky Way and Andromeda. The local group wasn't just drifting through space. It was moving with a speed far higher than could be explained by any structures nearby. The velocity measured was hundreds of kilometers per second relative to the cosmic microwave background. That number alone suggested a powerful gravitational force was at play. But the local group was only one piece of information. To understand the full gravitational environment, astronomers needed a much broader map. As surveys expanded, astronomers measured peculiar velocities for galaxies in various clusters. Some of the most informative came from the Virgo cluster, Hydra Centaurus, Norma, and others. These clusters, far larger than our local group, showed peculiar velocities pointing toward the same region. Their speeds varied based on distance, location, and the gravitational influences around them. But the pattern held. The direction remained consistent, reinforcing the idea that something massive existed in that part of the sky. Understanding peculiar velocities required scientists to accept that the universe is not uniform. Some regions contain more matter than others. The unevenness of matter creates regions of stronger gravity. Galaxies respond to this by accelerating toward denser areas. Peculiar velocities reveal where these dense areas lie, even when telescopes can't see them directly. They also show how strongly gravity shapes motion across enormous distances. The difficulty came in distinguishing different contributions to peculiar velocity. A galaxy might have motion influenced by several gravitational sources, not just one. Nearby clusters tug on it. Larger structures further away tug too. If these tugs align, the galaxy's peculiar velocity becomes strong. If they conflict, the motion becomes harder to interpret. Astronomers needed to map galaxies over huge areas and compare flows across broad distances to see which influences were dominant. When they did, a clear trend appeared. Peculiar velocities across our region of the universe pointed toward the same direction in sky coordinates, roughly the area inhabited by Hydra Centaurus and the zone where the Great Attractor was later placed. This wasn't an arbitrary location. It was the region where many galaxies had the largest deviations from expected expansion. Their peculiar velocities created a kind of gravitational signature. The signature suggested a large gravitational attractor that pulled galaxies in steadily. One of the remarkable aspects of peculiar velocity studies is how they reveal motion on scales too large to observe directly. A galaxy's peculiar velocity doesn't change noticeably over decades or even centuries. The movements are too slow to detect without careful measurements. Yet when collected in large numbers, these velocities form patterns that outline the shape of cosmic structure. It's similar to watching a slow-moving crowd from above. If you look briefly, it seems still, but if you compare positions over a long time, the direction becomes clear. The analysis of peculiar velocities also required accounting for observational limitations. Dust, gas, and stars in the Milky Way blocked some regions of the sky, making data incomplete. To fill these gaps, astronomers modelled the behaviour of galaxies based on surrounding regions. When they mapped peculiar velocities across the sky, they could estimate the flow in the blocked areas. These adjustments supported the idea that a massive gravitational influence lay behind the Milky Way's disk. Another challenge came from determining how peculiar velocities change with distance. If the Great Attractor were responsible for the motion, then galaxies closer to it should exhibit different peculiar velocities than galaxies farther away. Observations supported this. Galaxies at moderate distances showed strong peculiar velocities pointing toward the Great Attractor region. Those even farther away began to show velocities that continued beyond it in the direction of the Shapley Supercluster. This pattern supported the idea that the gravitational basin wasn't limited to one structure but spanned multiple regions. To better understand these flows, astronomers used statistical methods to smooth out individual variations. Each galaxy has its own local environment that can add noise to its velocity, but when velocities from thousands of galaxies are averaged, the larger pattern becomes clearer. This smoothing process revealed a flow that extended across a large portion of the nearby universe. The flow pointed toward a region of higher density that matched the expected location of the Great Attractor and continued toward Shapley. The importance of peculiar velocities grew as more data came in. They became a cornerstone of understanding cosmic structure because they provided insights into the distribution of dark matter. Dark matter does not emit light, but it contributes significantly to gravitational pull. The peculiar velocities reflected the presence of dark matter concentrated in clusters and superclusters. Regions with high peculiar velocities pointed to deep gravitational wells filled with dark matter and regular matter together. This made peculiar velocities one of the best ways to map dark matter indirectly. As peculiar velocity studies matured, astronomers built more sophisticated models that used these velocities to reconstruct the gravitational field around us. Instead of relying solely on observations of clusters, they combined data from galaxy surveys, cosmic microwave background measurements, and theoretical predictions of how matter should flow in a universe filled with dark matter. These reconstructions produced maps that resembled a topographical map of gravity. The region of the Great Attractor appeared as a low point, a gravitational basin where matter had accumulated over billions of years. These reconstructions also highlighted the role of voids. Voids, the large empty regions between filaments, contributed indirectly by allowing galaxies to escape their regions more easily. When a galaxy sat near a void, the lack of gravitational pull from that direction meant it was more strongly influenced by the mass on the other side. Peculiar velocities helped identify where these voids were located by showing how galaxies moved around them. The pattern showed that galaxies were being pushed away from voids and pulled toward denser regions, contributing to the overall flow toward the Great Attractor. One of the most revealing tests of peculiar velocity models came when astronomers compared them to gravitational reconstructions made using completely different methods. If peculiar velocities were truly mapping the gravitational field correctly, then simulations based on them should match simulations based on the distribution of visible galaxies. When these comparisons were made, the results aligned. The gravitational field inferred from peculiar velocities matched the gravitational field predicted by galaxy distribution. This gave scientists confidence that they had correctly understood the invisible pull. Even though peculiar velocities are essential for understanding the Great Attractor, they are not the whole story. They provide the first hints of its presence, and the general direction of the flow, but they do not fully reveal its structure. They need to be combined with surveys, simulations, and observations in other wavelengths to create a complete picture. But without peculiar velocities, astronomers might not have realized anything unusual was happening at all. The expansion of the universe could have concealed the drift, making the gravitational influences harder to detect. The mystery of peculiar velocities taught scientists that cosmic expansion is not the only major movement shaping the universe. The gravitational landscape plays an equally important role, guiding galaxies along paths determined by density variations. This understanding deepened as measurements improved, showing just how interconnected structures in the universe truly are. When astronomers finally accepted that peculiar velocities across our region of the universe were too large to be explained by known structures, it meant something important was missing from the map. Not a small detail, not a minor correction, but something significant enough to alter the motion of entire galaxy clusters. The search for that missing mass became one of the most persistent efforts in modern cosmology. It wasn't a search for a single object, it was a search for an entire gravitational environment that refused to show itself in ordinary light. And the more astronomers looked, the more they realized that this invisible influence wasn't hiding, because it was subtle. It was hiding because it lay behind one of the most inconvenient parts of the sky for observation. The region stood buried behind the dense spine of the Milky Way, a part of the sky filled with dust, gas, and countless stars. This crowded area blocked the view of anything beyond it. For astronomers, it was like having a large section of the cosmos behind a thick fog. You could point a telescope straight at it and see only the foreground. The galaxies behind it were not absent. They were simply concealed by the Milky Way's disk. And yet, based on the observed motions of galaxies across the sky, something major sat in that hidden area. Something with enough mass to shape the motion of thousands of galaxies spread across a vast region. This created a challenge unlike most others in cosmology. The missing structure couldn't be observed directly using traditional optical telescopes. It had to be inferred from indirect evidence, from the way other galaxies responded to its presence. The hunt began with a simple question. If something is pulling us and many surrounding galaxies in a particular direction, where is it, and how large must it be to have such an effect? The answer required breaking apart the gravitational landscape into all of its contributing pieces. Astronomers already knew that nearby clusters such as Virgo exerted some pull. Hydra and Centaurus added their influences. The Norma cluster seemed to play a noticeable role once it was detected in other wavelengths. But when all these known structures were accounted for, the gravitational pull still fell short. The peculiar velocities were too large. The drift was too strong. Either the known clusters were more massive than believed, or something else, something larger, was contributing significantly. The most likely explanation was that the hidden region behind the Milky Way contained massive clusters that had not yet been catalogued. But even if clusters existed there, would they be large enough to explain the full motion? That uncertainty drove astronomers to examine the region using every wavelength available. Optical light was nearly useless due to dust obscuration. Infrared surveys began to uncover hints of galaxies. Radio observations added new detections. X-ray telescopes found hot gas in clusters that were invisible in optical wavelengths. Each method produced partial glimpses, like pieces of a puzzle that didn't show the entire picture. At first, these surveys revealed clusters that had been entirely hidden, and some of them were impressively large. The Norma cluster stood out as one of the most significant. Located near the region predicted by peculiar velocity studies, Norma contained a dense concentration of galaxies bound together by gravity. Its mass was substantial enough to contribute to the gravitational basin affecting our region. But even Norma didn't fully close the gap. Its influence explained part of the drift, but not the entirety of it. This led astronomers to widen the search. If the mass behind the Milky Way wasn't enough on its own, perhaps the region just beyond it played a larger role. galaxy surveys extending farther into the cosmos started to identify structures in the same direction as the Great Attractor, but well past the zone of avoidance. These newly discovered superclusters contained hundreds of galaxies, in addition to large amounts of dark matter. The discovery of these structures shifted attention from the idea of a single massive object to the possibility of an extended region of high density. Instead of searching for one hidden mass, astronomers began to look for an entire sequence of masses arranged along the same direction. This shift in understanding was a turning point. The flow of galaxies didn't point to a narrow target. It pointed toward a broad zone, and that implied the gravitational pull wasn't coming from a local anomaly, but from a large-scale feature of the cosmic web. The Great Attractor became understood not as a single cluster, or even a single supercluster, but as a gravitational basin created by multiple massive structures. This idea was supported by cosmological simulations. When scientists modelled the distribution of matter across the universe and then let gravity act over billions of years, the simulations naturally produced large-scale flows similar to what we observe. The flows pointed toward regions where mass had accumulated into dense clusters and superclusters. These simulations also showed that the motions of galaxies were influenced by both nearby structures and more distant ones. The combination of these influences created bulk motions over large regions. With this in mind, astronomers began to reconsider the region where the Great Attractor was thought to lie. Hydra Centaurus and Norma were part of it, but beyond them lay a still larger structure, the Shapley Supercluster. Located farther along the same general direction, Shapley contained dozens of massive clusters. Its total mass far exceeded that of Hydra Centaurus. If Shapley contributed strongly to the drift, that would explain why the gravitational pull seemed so strong. It would also explain why galaxies beyond the Great Attractor continued moving in the same direction instead of stopping. This idea gained support when peculiar velocity data showed that the flow of galaxies did not peak at the distance of the Great Attractor. Instead, it continued beyond it, increasing farther out. This indicated that the gravitational basin was deeper in that direction than initially believed. The Great Attractor was not the final destination, but part of a larger gravitational descent. The flow pointed toward the Shapley supercluster as the deepest part of the potential well in that region of space. This discovery didn't diminish the importance of the Great Attractor. Instead, it clarified its role. It serves as a large gravitational feature that forms a kind of ridge in the cosmic landscape. Galaxies on our side of that ridge fall toward it, but those that pass through continue toward Shapley. The combined influence of Hydra Centaurus, Norma and Shapley forms an extended gravitational environment that shapes the motion of galaxies across hundreds of millions of light years. The hunt for the hidden mass became less about searching for a single concealed object and more about mapping an entire region of gravitational influence. This required detailed reconstructions of galaxy positions and velocities. Astronomers used sophisticated mathematical techniques to infer the distribution of matter from the measured motions. These reconstructions showed areas of high density where clusters and superclusters existed. They also revealed voids, large empty regions, that influenced motion by creating zones of lower gravity. The combination of these dense and sparse regions formed a complex pattern of motion that matched what peculiar velocity studies observed. One of the most important contributions came from redshift surveys that mapped the positions of galaxies across large sections of the sky. These surveys created three-dimensional maps showing how galaxies are arranged in filaments and clusters. When these maps were combined with velocity data, astronomers could trace out the flow lines that galaxies followed. These flow lines pointed directly toward the region of the Great Attractor and beyond toward Shapley. They formed a coherent pattern, not a collection of random motions. Another layer of evidence came from examining the motions of the cosmic microwave background. The dipole pattern in the background radiation revealed that our entire region of the universe was moving at a significant speed toward the Great Attractor region. This motion could not be explained by local structures alone. It required mass on a much larger scale. When the contributions of Hydra Centaurus and Norma were added to those of Shapley, the numbers matched the observed dipole. This reinforced the idea that the hidden mass was not limited to what lay behind the Milky Way. The gravitational pull came from a combination of structures that extended far beyond our initial view. The hunt also revealed the significance of dark matter in shaping these motions. Visible galaxies and clusters only account for a fraction of the total mass in any region. Dark matter contributes most of the gravitational influence. By mapping the motions of galaxies and reconstructing the gravitational field, astronomers could infer where dark matter must be concentrated. The hidden mass behind the Great Attractor region includes large amounts of dark matter spread across clusters and filaments. This dark matter plays a central role in creating the gravitational pull we observe. As the picture became clearer, astronomers developed a more detailed understanding of the cosmic web in this part of the universe. They identified the Laniakea Supercluster, a massive structure that includes the Milky Way, Virgo, Hydra Centaurus, and the Great Attractor region. Laniakea spans hundreds of millions of light years. Its structure is defined by the flow of galaxies within it. The gravitational center of this supercluster lies near the Great Attractor, but the flow lines extend beyond it toward Shapley. This means that the Great Attractor lies within a larger structure and contributes to the overall motion of our region. The discovery of Laniakea reframed the entire discussion. The hunt for the hidden mass had revealed not just one gravitational feature, but an entire supercluster defined by the motion of galaxies. The Great Attractor was no longer seen as a single anomaly. It became part of the gravitational core of Laniakea. Its mass, combined with the surrounding structures, created a region where galaxies flowed inward, and beyond that region, the gravitational reach of Shapley continued to draw galaxies along. This realization helped explain why earlier attempts to pinpoint the Great Attractor produced conflicting results. The region wasn't a single cluster. It wasn't a compact object. It wasn't even a single supercluster. It was a complex gravitational environment where multiple structures contributed to the overall pull. Attempting to locate it precisely using only optical observations meant missing most of the mass. Only by combining multiple observational techniques and analysing motion rather than appearance did astronomers uncover the full picture. The hunt for the hidden mass demonstrated the power of looking at the universe through motion instead of through light alone. Galaxies acted like markers drifting along the gravitational contours of the cosmic web. Their movement mapped out the unseen shapes of matter. This approach revealed massive structures where telescopes saw little. It showed how the universe hides its depths behind natural obstacles, and it made clear that to understand cosmic structure, astronomers must use every tool available, from infrared to radio to X-ray, and from simulations to velocity reconstructions. When astronomers finally gathered enough data to trace the flow of galaxies across a vast region of space, they noticed something that redefined how we understand our position in the universe. The motions weren't scattered. They weren't independent. They weren't even localized. Instead, they formed broad, steady pathways that converged into a larger structure. These pathways revealed that the Milky Way, along with thousands of other galaxies, belonged to something much larger than anyone had expected when the study of cosmic flows first began. That structure eventually came to be known as the Laniakea Supercluster, a region so vast and so interconnected that describing it requires tracing not lines of light, but lines of motion. The name Laniakea means immeasurable heaven, and while astronomical names don't usually influence the science itself, this one captures the scale in a way that numbers alone struggle to convey. The structure spans hundreds of millions of light years. It contains tens of thousands of galaxies. It incorporates several major clusters, including Virgo, Hydra Centaurus, and the region associated with the Great Attractor. But the most important part of defining Laniakea is not the list of galaxies or clusters within it. It's the way these galaxies move. Their motions reveal the gravitational landscape that binds them together. They show how matter flows inward along the cosmic web, guided by gradients of density rather than by isolated objects. This flow-based definition marks a shift from older ways of understanding superclusters. Historically, superclusters were identified by counting galaxies, or by mapping regions of high brightness. But those definitions were limited. They didn't account for the gravitational environment. They didn't consider how galaxies moved. They simply outlined areas where matter was concentrated. The flow-based approach offered something deeper. It allowed astronomers to define a structure not by appearance but by behavior, by following the way galaxies drift under the influence of gravity. When researchers applied this method to the local region of the universe, they found that the Milky Way and its neighbours weren't just sitting in the Virgo supercluster as previously thought. Instead, Virgo itself was only part of a larger complex of flows. All of these flows converged toward a central region located near the Great Attractor. That area served as the gravitational core of a supercluster far larger than Virgo alone. The Milky Way wasn't merely near one cluster. It was part of an enormous gravitational domain that extended across several major structures. Understanding our place within Laniakea required looking at the directions in which galaxies move. Every galaxy within the region has a peculiar velocity, a deviation from pure expansion. When these velocities were plotted across space, they formed streamlines, paths that galaxies follow as they drift inward. These streamlines curved and bent but eventually converged toward a common basin. That basin defined the central region of Laniakea. Everything within this network of flows is part of the same gravitational domain. Galaxies inside the boundary move toward the same region. Galaxies outside the boundary flow toward different basins, belonging to other superclusters. This new way of defining superclusters changed the perspective of astronomers who had spent decades studying local structures. It revealed that our galaxy is part of a dynamic system. We aren't anchored to a fixed structure. We drift along a gravitational slope, moving slowly but persistently toward the center of this enormous region. Our motion is not random. It is guided by the larger gravitational forces around us. And those forces come not from a single massive object, but from the combined influence of clusters, dark matter, and the distribution of galaxies across a massive area. One of the most significant aspects of Laniakea is the role of the Virgo cluster. Virgo has long been recognized as the nearest major cluster to the Milky Way. It contains thousands of galaxies and exerts a noticeable pull. But Laniakea shows that Virgo is only one of the gravitational features shaping our motion. The Milky Way is not falling directly into Virgo. Instead, it moves in a direction influenced by both Virgo and larger structures beyond it. The flow maps show that galaxies move toward Virgo from some directions, but also move past it toward the deeper gravitational basin associated with the Great Attractor. Virgo is a landmark within Laniakea, but it is not the final destination of the drift. The Hydra Centaurus region plays a more central role in defining Laniakea. Hydra and Centaurus contain clusters large enough to affect the motion of galaxies on a greater scale than Virgo. Together, they form a major convergence zone. Galaxies from many directions drift toward this region. It sits near the boundary of the zone of avoidance, where the Milky Way blocks the view. This made it difficult to map Hydra Centaurus in detail for many years. But once astronomers studied the region using infrared, radio, and X-ray observations, they identified clusters with enough mass to account for a significant portion of the pull-shaping local flows. The understanding of Hydra Centaurus deepened further when the Norma cluster was discovered behind the Milky Way's disk. Norma lies at the heart of the gravitational basin associated with the Great Attractor. It is one of the densest clusters in the region, filled with matter both visible and dark. Its gravitational influence helps explain why the flow of galaxies bends toward that direction. The Norma cluster, along with Hydra and Centaurus, forms part of the core region of Laniakea, but the story doesn't end there. When astronomers extended flow analyses farther out, they found that the most massive structure influencing the region lies beyond the Great Attractor. The Shapley Supercluster, located farther in the same direction, contains enough mass to contribute significantly to the motion of galaxies across Laniakea. Shapley sits outside the boundary of Laniakea itself, but its influence reaches inward. This means that while Laniakea defines the region of space where galaxies flow toward the Great Attractor basin, additional structures beyond it contribute to the overall pull. This is one of the reasons the motions observed are so strong. The boundaries of Laniakea were drawn by finding the point where galaxy flows diverge. Galaxies on one side of the boundary move toward the Great Attractor. Galaxies on the other side flow toward different basins, such as the one associated with the Perseus-Pisces supercluster. This separation line allowed astronomers to define the volume of space dominated by the Great Attractor region. Within that volume, the gravitational landscape guides galaxies toward the same central basin. Outside that volume, flows follow different routes. This method of defining boundaries by motion gives a dynamic picture of the universe. It shows that superclusters are not static clumps of galaxies. They are regions shaped by gravity, where matter flows inward continually. The flows move slowly because distances are enormous and gravitational forces weaken with distance, but the pattern remains steady over billions of years. Galaxies travel along cosmic filaments, the thread-like structures of gas, stars, and dark matter that connect clusters. These filaments create pathways that guide galaxies toward the center of Laniakea. The Milky Way sits on one of these filaments. Our galaxy doesn't drift freely through space. It follows a path shaped by the gravitational field of the larger structure around it. This path leads toward the Great Attractor, but because Shapley lies farther along the same direction, the flow eventually extends beyond the Great Attractor region. The interior of Laniakea contains clusters and filaments, all contributing to the motion. The outer region feels the influence of even more massive structures beyond it. Our place within Laniakea is not central. We are positioned on the outskirts of the supercluster, closer to the edge where flow lines begin to diverge. This means our galaxy is part of the structure but not deeply embedded within its densest regions. The central regions of Laniakea contain far greater concentrations of mass. Galaxies there move more directly toward the gravitational basin. Our motion is affected but not dominated as strongly as those deeper within the structure. This explains why the peculiar velocities of galaxies near us are modest, compared to those closer to the core. Another important insight from Laniakea is the realization that superclusters are not gravitationally bound in the traditional sense. The expansion of the universe is strong enough to prevent these enormous regions from collapsing completely. Instead, they are flow-defined structures. Their boundaries are determined by the gravitational influence they exert on galaxies, not by the galaxies being bound together tightly. This means that while galaxies flow toward the center of Laniakea, the region as a whole is still expanding. Gravity slows that expansion locally, but does not reverse it entirely. This makes Laniakea a transitional structure in the cosmic hierarchy. It is large enough to shape motion, but not compact enough to collapse into a single cluster. It is influenced by structures beyond its boundaries, yet it maintains a recognizable gravitational basin that defines its identity. Understanding these properties helped astronomers refine how such enormous structures should be described. Instead of imagining superclusters as closed systems, they became understood as dynamic regions shaped by the continuous flow of matter. The discovery of Laniakea also reshaped the story of the Great Attractor. What once appeared to be a solitary anomaly turned out to be part of a vast interconnected gravitational environment. The pull we experience is not isolated. It comes from the entire arrangement of matter within Laniakea, combined with contributions from Shapley beyond it. This helped resolve the confusion about the strength of the drift. The motion isn't caused by a single cluster, it is caused by an entire gravitational network. As astronomers continue to refine maps of cosmic flows, the structure of Laniakea becomes clearer. The boundaries sharpen, the filaments stand out more distinctly, the clusters are placed more precisely. but the basic understanding remains consistent. The Milky Way belongs to a supercluster defined not by brightness or shape, but by the gravitational motions that guide thousands of galaxies along common paths. This view of our place in the universe offers something that older models didn't capture. It shows that our galaxy moves as part of a larger system. It shows that local motions are part of regional motions, which in turn are part of motions shaped by even larger structures. It connects our understanding of galaxy clusters to the broader cosmic web, and it prepares the ground for understanding how the gravitational pull of the Great Attractor ultimately fits into the full hierarchy of cosmic structures. When astronomers mapped the motions of galaxies across the region now known as Laniakea, they found that visible matter alone couldn't explain what they were seeing. The flows were too organized, the speeds were too high, the gravitational basin at the center of the region appeared too deep for the amount of mass that telescopes could identify. Clusters like Virgo, Hydra, Centaurus and Norma contributed significantly, yet even their combined weight fell short. Something else had to be shaping the structure of the supercluster, something more massive, more widespread, and far more difficult to detect. The search for that missing contribution inevitably led back to dark matter, the invisible component that dominates the mass of the universe. Even long before the Great Attractor was identified, dark matter had been recognized as a major ingredient in cosmic structure. Galaxy rotation curves hinted at its presence. Cluster dynamics pointed to mass that wasn't visible. Gravitational lensing revealed distortions in light caused by matter that emitted no radiation. But understanding how dark matter influenced local flows required a different perspective. Instead of measuring how galaxies rotated within their own halos, astronomers had to consider how dark matter shaped the entire large-scale gravitational field across hundreds of millions of light-years. This broader view made it clear that dark matter wasn't merely a supporting detail. It was the backbone of the structure itself. Visible galaxies marked the locations of dense regions, but they represented only the brightest fraction of the total mass. Most of the real weight, the mass responsible for guiding galaxies along the gravitational pathways that defined Laniakea, was dark matter arranged in vast interconnected halos. These halos overlapped, merged, and extended along the filaments of the cosmic web, forming a framework far more substantial than anything visible. Understanding dark matter's role in the Great Attractor began with recognizing how galaxies move inside a dark matter-dominated universe. Instead of drifting randomly or obeying only the expansion of space, galaxies respond to the gravitational potential shaped by dark matter. Where dark matter is dense, galaxies fall inward. Where it is sparse, galaxies drift more freely. This creates corridors of motion along the filaments and channels between voids. The flows mapped across Laniakea trace these gravitational pathways, revealing the shape of the underlying dark matter distribution. When astronomers calculated the mass needed to produce the observed flows, they found that visible matter could account for only a small portion. Even the most massive clusters, when considered without dark matter, would fall far short of explaining peculiar velocities measured across local regions. But once dark matter was included in the models, the gravitational field aligned with observations. The peculiar velocities matched. The flow lines traced by galaxies curved in the exact directions expected from dark matter concentrations. And the gravitational basin associated with the Great Attractor gained the depth required to account for the drift of thousands of galaxies. What made this even more convincing was the consistency across different methods. Gravitational lensing surveys showed that invisible mass was concentrated in the same regions that peculiar velocity studies pointed toward. X-ray observations of hot gas in galaxy clusters revealed that the gas was bound within halos much more massive than their visible stars suggested. Large-scale simulations of cosmic structure formation demonstrated that dark matter naturally forms regions similar to the Great Attractor, where matter sinks into gravitational basins shaped primarily by invisible mass. This agreement between observations and theory made it clear that dark matter wasn't just a convenient addition, it was essential. The structures responsible for the gravitational pull affecting our region couldn't exist without dark matter. The density of dark matter in and around the Great Attractor had to be enormous. It filled the Norma cluster's halo, it extended through Hydra Centaurus, it stretched along filaments connecting dozens of smaller clusters, and beyond the Great Attractor, the same dark matter framework extended into the Shapley Supercluster, whose mass accounted for much of the additional pull that early estimates had failed to explain. The scale of this influence becomes clearer when considering how dark matter behaves over time. Unlike ordinary matter, dark matter does not radiate, cool, or collapse into small structures easily. It forms giant halos long before galaxies populate them. These halos merge and grow into even larger structures, eventually forming supercluster-scale frameworks. The visible galaxies that form within these halos simply trace the underlying gravitational architecture, so when astronomers mapped the flow of galaxies toward the Great Attractor, they were effectively mapping the flow of matter into a large dark matter concentration formed billions of years earlier. This historical perspective shows that the gravitational environment of Laniakea has been shaped by dark matter since the earlier stages of cosmic structure formation. The flows we observe today are not sudden. They are the cumulative result of billions of years of slow motion governed by dark matter density variations. Even the peculiar velocities of galaxies represent movements too slow to observe directly on human timescales, yet they reflect long-term gravitational trends shaped by the dark matter distribution. The quiet influence of dark matter also explains why the Great Attractor remained hidden for so long. Visible matter could not account for the strength of the gravitational pull, and the central region lay behind the zone of avoidance. But dark matter is not blocked by dust. Its gravitational influence reaches across space regardless of observational obstacles. The galaxies responded to its presence even when telescopes could not see the structure producing the pull. Once astronomers measured that response, they could reconstruct the dark matter distribution indirectly. This is why peculiar velocities became such valuable clues. They revealed gravitational patterns that could not be explained without dark matter. As researchers refined their maps, they discovered that the largest portion of the mass shaping the Great Attractor region wasn't contained in individual clusters, but in the dark matter filaments connecting them. These filaments act like bridges of gravitational influence. They guide matter toward dense clusters and link entire regions across vast distances. The structure of Laniakea, as traced by galaxy flows, reflects the network of these filaments. The Milky Way is connected to Virgo by one such filament. That filament connects to Hydra Centaurus. Hydra Centaurus connects to Norma, and beyond Norma, filaments extend toward Shapley. This interconnected network creates the continuous gravitational environment responsible for the drift of galaxies. Another important clue comes from studying voids. Voids are enormous regions with very little matter, including dark matter. Galaxies near these voids feel less gravitational pull from the void side and more from the denser side. This indirect effect contributes to the overall motion. The Laniakea supercluster contains several large voids surrounding its filaments. As dark matter congregates in the filaments and clusters, the voids become gravitationally weak areas, effectively enhancing the inward drift toward the central region. The presence of these voids strengthens the role of dark matter even further by making the dense areas more influential in guiding motion. When dark matter simulations are run without including structures like Shapley, the flows don't match observations. When Shapley's dark matter contribution is added, the flows become consistent with the measured peculiar velocities. This alignment strengthens the idea that Shapley plays a major role, even though it lies far beyond the Great Attractor. The dark matter in Shapley's region adds gravitational pull that combines with the mass in Hydra Centaurus and Norma, creating the large-scale flow extending across Laniakea. This combination explains why the drift continues past the Great Attractor instead of stopping there. One of the most revealing aspects of dark matter's quiet influence is how it makes the universe more predictable. The motions of galaxies, once mysterious and seemingly inconsistent, align perfectly when dark matter is included. The gravitational landscape becomes coherent. Flow lines converge where they should. Boundaries between superclusters appear naturally, and the peculiar velocities that once seemed puzzling now make sense. Dark matter provides the missing weight that completes the picture. It also explains why large structures like Laniakea remain stable, even though the universe continues to expand. Dark matter's gravitational pull slows the expansion locally. It binds clusters and filaments enough to maintain their shape over enormous distances and timescales. Without dark matter, the supercluster would not hold together as a coherent flow. The filaments would disperse. The gravitational basin would be shallower. The flow toward the Great Attractor would be weaker. Dark matter gives the structure its depth and durability. Understanding dark matter's influence also deepens our awareness of how much of the universe remains invisible. The visible galaxies, clusters, and superclusters represent only a small percentage of the total mass. The rest is hidden, contributing silently to the forces shaping cosmic structure. The Great Attractor would be impossible without dark matter. Laniakea would be impossible without dark matter. Even the simple fact that the Milky Way moves toward a particular region cannot be explained without including this unseen component. The quiet nature of dark matter is part of what makes its influence so striking. It doesn't emit light. It doesn't absorb light. It doesn't react with ordinary matter in familiar ways. Yet its gravitational influence is powerful enough to guide entire regions of space. The galaxies around us are drifting through a dark matter-shaped landscape, following paths laid out by invisible mass. The Great Attractor is a gravitational feature defined more by dark matter than by the galaxies within it. The same is true for the superclusters beyond it. As astronomers continue to refine measurements of cosmic flows, dark matter remains the key ingredient that ties the evidence together. It explains the stability of filaments. It explains the distribution of clusters. It explains the shape of gravitational basins. And it explains why the motion of the Milky Way and many galaxies around us remains so steady. When astronomers first realized that the gravitational influence shaping our region of the universe pointed toward an area hidden behind the Milky Way, they faced a challenge unlike anything that had come before. They weren't simply trying to understand faint galaxies, distant clusters, or structures at the edge of observational limits. Instead, they had to look through something that wasn't just far away but directly in the way. The zone of avoidance, the band of sky obscured by the dense plane of the Milky Way, had long been a region where astronomers collected few measurements and made few assumptions. It wasn't ignored because it was uninteresting. It was ignored because the galaxy itself made the area nearly impossible to study. For decades, this region created a blind spot in our map of the universe. Thick clouds of dust and gas absorb visible light, scattering it before it can reach Earth. Stars crowd together so densely that background galaxies are almost impossible to distinguish. This part of the sky formed a barrier, a place where the known universe appeared to end not because it truly ended, but because our tools couldn't see past the interference. When the earliest surveys of large-scale cosmic structure were made, astronomers simply left the zone of avoidance blank, treating it as a gap rather than a region that needed decoding. But as measurements of peculiar velocities strengthened the case for the Great Attractor, it became clear that the gap was not just a minor inconvenience. It contained something crucial, something massive, something that affected the motion of galaxies across an enormous span of space. The gravitational influence coming from that direction was too strong to be ignored. It was as if a mountain range lay hidden behind a thick fog, shaping the landscape even though no one could see it. The only way to understand the region fully was to find a way to look through the fog, using methods that didn't rely solely on visible light. The effort to peer into the zone of avoidance required changing the kinds of tools astronomers used. Instead of depending on optical telescopes, they began exploring wavelengths capable of passing through dust more easily. Infrared observations became an early priority. Infrared light interacts differently with dust, allowing it to travel through the disk of the Milky Way with far less scattering. When infrared surveys began scanning the hidden region, they revealed galaxies that had never appeared in optical charts. These galaxies offered the first glimpses into what lay behind the Milky Way's barrier. Infrared observatories detected the faint glow from stars within concealed galaxies, uncovering clusters and groups previously unknown. While the images were not always sharp or detailed, they were unmistakable evidence that the zone of avoidance contained a vast number of galaxies. It wasn't an empty region at all. The Milky Way's dust had merely kept them hidden from view. Each infrared detection provided a point of reference, a location to revisit using other wavelengths and methods. Radio observations added an even more powerful tool. Hydrogen gas emits radio waves at a specific frequency, and those waves can pass through dust unimpeded. Large radio telescopes began scanning the zone of avoidance for signals from hydrogen. Every detection of hydrogen gas pointed to a galaxy or structure beyond the Milky Way's midplane. And unlike optical or even some infrared methods, radio observations could measure the motion of the gas directly through Doppler shifts. This allowed astronomers not only to detect galaxies, but to determine how fast they were moving and in which direction. As radio surveys expanded, a picture emerged that was richer and more complex than expected. The region behind the zone of avoidance wasn't just dotted with galaxies. It contained entire clusters, large structures with hundreds of galaxies each. These clusters weren't scattered randomly. They formed part of the same network of filaments that shaped the rest of the cosmic web. The zone of avoidance had concealed a substantial section of this web, including portions of major structures linked to the Great Attractor. One of the most significant discoveries from these surveys was the identification of the Norma cluster, a dense and massive cluster sitting in precisely the region where peculiar velocity measurements had pointed. Norma contained large amounts of dark matter, as well as numerous galaxies tightly bound together. Its mass contributed significantly to the gravitational basin shaping the drift of galaxies across Laniakea. Finding Norma confirmed that the zone of avoidance hid not just faint galaxies, but major structures capable of influencing motion across hundreds of millions of light-years. Even with infrared and radio observations, some regions within the zone of avoidance remained challenging. Dust can still obscure certain wavelengths, and the extreme brightness of the Milky Way's core complicates measurements in nearby areas. To overcome these obstacles, astronomers turned to X-ray observations. Hot gas in galaxy clusters emits X-rays, and these high-energy photons can travel through regions that block visible light. X-ray observatories began scanning the zone of avoidance for signs of hot gas that would reveal the presence of hidden clusters. These scans uncovered several additional clusters, some of which contained enough mass to contribute meaningfully to the region's gravitational influence. The combination of X-ray, radio, and infrared discoveries began filling in the blank spaces on the cosmic map. After decades of treating the zone of avoidance as an observational void, astronomers were finally illuminating the structures behind it. The discoveries were not isolated. They fit into a pattern, connecting to the Hydra Centaurus region, linking to Norma, and extending toward regions associated with the Shapley Supercluster. As more of the hidden structures were uncovered, astronomers refined their models of the gravitational environment around the Great Attractor. The mass in the concealed region turned out to be substantial, but not sufficient by itself to explain the full motion of galaxies. This reinforced the understanding that the Great Attractor was not a single object. It was part of a larger gravitational basin shaped by multiple clusters and superclusters. The zone of avoidance had hidden important pieces of the puzzle, but the full picture required connecting those hidden pieces to structures beyond them. The process of mapping the zone of avoidance wasn't straightforward. The region remains one of the most complex areas to survey. Dense star fields create confusion in identifying sources. Background galaxies often appear faint and difficult to distinguish. Some portions of the area remain poorly resolved even today, but each generation of surveys brings new clarity. Instruments sensitive to different wavelengths complement one another. Radio surveys reveal hydrogen-rich galaxies, infrared maps detect old stars, X-ray studies highlight massive clusters. Together, these methods reduce the uncertainty that once defined the region. One important realization that emerged during this process was that the structures behind the zone of avoidance are not isolated from the rest of the cosmic web. They form part of a continuous network that stretches across the region of the Great Attractor. The filaments beneath the obscured region connect to the larger framework of Laniakea. These connections explain why the gravitational pull from the region is so strong. The Milky Way's disk blocked the view, but not the influence. The dark matter halos behind the zone of avoidance extended seamlessly into the broader structure. The flows of galaxies traced those underlying connections even when telescopes could not see them. The zone of avoidance also provided a unique testing ground for methods used to infer hidden mass. By comparing the observed motions of galaxies with the inferred gravitational environment, astronomers could test whether their models accurately predicted where unseen structures should lie. In many cases, predictions made from peculiar velocity studies matched later observations from infrared, radio, or X-ray surveys. This consistency strengthened confidence in the methods used to map dark matter and cosmic structure more generally. While surveying this region, astronomers also became more aware of how much of the universe remains unobserved. Even now, portions of the zone of avoidance contain objects that have not been clearly identified. Some areas are so dense with Milky Way stars that distinguishing background galaxies remains a challenge. But the vast improvement in observational tools means that fewer secrets remain than in the early days of cosmic mapping. The hidden region is no longer a complete mystery. It is a mostly uncovered section of a larger structure, its outlines now traced through multiple wavelengths and careful modelling. The discoveries in the zone of avoidance helped explain why early attempts to identify the Great Attractor had produced confusing results. Different teams measured slightly different positions and distances for the source of the gravitational pull. Some placed it closer, some placed it farther. Some believed it was linked entirely to Hydra Centaurus, while others thought it was tied to deeper structures. The reason for these discrepancies became clear once the hidden clusters were revealed. The mass responsible for the pull wasn't concentrated in a single point. It was distributed across a region filled with clusters, filaments, and dark matter. The Milky Way's obstruction had prevented astronomers from seeing the full distribution, leading to incomplete conclusions. As the surveys continued, astronomers realized that the zone of avoidance had masked not only portions of the Great Attractor, but also parts of the pathways leading to the Shapley Supercluster. Some of the filaments connecting the Great Attractor to Shapley passed through the obscured region. When these filaments were identified through infrared and radio observations, the large-scale flow became even clearer. Galaxies weren't just falling into the Great Attractor. They were passing through it, continuing along the network toward Shapley. This helped resolve the long-standing question of why peculiar velocities increased beyond the distance of the Great Attractor. By filling in the missing information within the zone of avoidance, astronomers could create more accurate maps of the overall flow. The boundaries of Laniakea became more sharply defined. The motion of galaxies within the supercluster became easier to interpret, and the large-scale gravitational field that shapes our region of the universe became more coherent. What once looked like a mysterious and contradictory set of observations now formed a consistent picture. The effort to peer into the zone of avoidance wasn't just a matter of filling in a blank. It demonstrated the importance of observing the universe with multiple tools. Each wavelength revealed something different, something complementary. Together they created a more complete view of cosmic structure. The hidden region behind the Milky Way showed that even areas long considered inaccessible could be studied if astronomers used the right methods and were willing to look beyond traditional tools. When astronomers finally traced the motions of thousands of galaxies toward the same region of the sky and revealed enough of the structures hidden behind the Milky Way to identify major clusters, there was still an unanswered question at the center of the investigation. The observations revealed a gravitational basin, a convergence zone where galaxy flows bent inward, but they didn't reveal a simple object or a single defining core. The region behaved like a gravitational center, and yet resisted being defined by a single dense peak of mass. That contradiction made the heart of the Great Attractor one of the most puzzling features ever studied in extragalactic astronomy. Despite decades of work, the area did not present itself like the center of a cluster such as Virgo, where one can point to a dense core filled with galaxies and hot gas. Instead, the region gave off mixed signals. Some surveys showed concentrations of galaxies, others revealed sparse stretches that didn't look like a traditional cluster core at all. Sometimes the results pointed to the Norma cluster as the most important piece. Other times they suggested that the influence extended well beyond it. The region refused to behave like something simple and contained. It was elusive, not because it was mysterious in a supernatural sense, but because the environment did not conform to familiar expectations. Understanding why required looking at the Great Attractor as a gravitational feature rather than as an object. Instead of behaving like a bright beacon that organizes everything around it, the region acts more like a low-pressure area in a weather system, drawing flows inward from all directions. The galaxies that respond to that gravitational landscape are following a pattern shaped by mass that is spread out rather than concentrated. The center is not a pinpoint. It is a zone where competing influences overlap. This is why attempts to define one central cluster never fully captured the true nature of the region. The Norma cluster remains the most obvious anchor point in this area. Norma is massive, dense, and sharply defined by X-ray observations. It contains hundreds of galaxies, vast amounts of hot gas, and a dark matter halo large enough to influence motion across a wide area. It sits nearly at the geometric center of the earliest flow maps. Its mass is consistent with a major role in bending galaxy paths. But even when Norma's influence is accounted for, the gravitational strength required to match observed velocities extends beyond what Norma alone can provide. The cluster is important, but it is not enough. It is part of the core, yet not the entire core. What surrounds Norma complicates the definition further. Instead of dropping into empty space, the region around the cluster contains a web of filaments connecting Hydra Centaurus, Centaurus proper, and additional clusters in the same general region. These filaments spread out like branches, pulling galaxies along them toward the deeper basin. They contain dark matter, dwarf galaxies, small groups, and many structures too faint to be catalogued in early surveys. The gravitational sum of these filaments contributes significantly to the pull of the Great Attractor. But the distribution is irregular. Some filaments are thick and dense, others are thin. This unevenness creates a gravitational environment without a single dominant peak. To understand the elusive heart of the region, astronomers had to move beyond the familiar idea of a cluster core and instead imagine the environment as a merging zone. Over cosmic time, clusters fall toward one another. Filaments bring in matter from many directions. Voids expand and push galaxies inward. In such a setting, the center becomes a constantly evolving region, where matter accumulates unevenly. Norma may represent one major concentration, but Hydra Centaurus contributes from another direction. Farther out, additional mass from the direction of Shapley pulls the entire region into a deeper basin. These overlapping influences create a gravitational intersection rather than a single, localized center. This understanding required scientists to adopt models that treat the Great Attractor as a dynamic feature. The gravitational basin is not something fixed and simple. It formed gradually over billions of years as matter flowed along filaments. Early in the universe, before galaxies as we know them existed, dark matter began clumping in certain regions, creating the seeds of what would become the Great Attractor. As time passed, these clumps merged, forming larger halos and attracting ordinary matter. The result was not a single smooth structure, but a web of influence stitched together through the accumulation of mass. The elusive heart becomes easier to understand if one imagines this region as a crossroads of cosmic structure. Multiple flows approach from different directions. They converge because the gravitational landscape gives them no choice. The Great Attractor is not something separate from these flows. It is defined by them. Its presence is revealed by the motion of galaxies rather than by a bright cluster at its centre. The galaxies moving toward the region trace out the gravitational topography, outlining the basin even when the mass distribution within it remains irregular or difficult to detect directly. Attempts to identify the precise centre often led astronomers to re-evaluate what they considered a centre in the first place. The deepest part of the gravitational well may not be where visible matter appears strongest. Dark matter contributes heavily to the shape of the well, and dark matter does not always align perfectly with visible galaxies. In some simulations, the peak of the gravitational field lies slightly offset from the peak of galaxy density. This could explain why the Norma cluster looks central, but not perfectly aligned with calculations of the flow's deepest point. The core is a blend of influences, not a spot one can easily mark with a single coordinate. The Milky Way's position relative to this region added further complexity. Because the zone of avoidance hides so much, astronomers had to infer the distribution of mass using motion rather than direct imaging. That meant that early estimates of the centre shifted repeatedly as new data came in. One year the core appeared to lie near Norma, another year it appeared slightly offset. Later, new surveys revealed additional structures in the same general direction, leading to recalibrations. These shifts didn't indicate errors in the earlier work. They reflected the real complexity of the gravitational landscape. The core was never a single object. It was an extended region that appeared differently depending on which wavelengths and survey depths were used. The interaction between the Great Attractor and the Shapley Supercluster also shaped the elusive nature of the region. Shapley lies farther along the same path, and its mass is so great that it affects the gravitational environment all the way back through the Great Attractor. This means the flows toward the Great Attractor do not stop there. They continue past it. In that sense, the Great Attractor sits on the slope of an even larger gravitational descent. Its position is similar to a plateau on the side of a mountain. It is part of the larger structure but not the lowest point. This is why attempting to treat the Great Attractor as a single destination often led to confusion. The galaxy flows did not converge on it and stop. They passed through, revealing a deeper basin farther away. This idea transformed the understanding of the region. Instead of seeing the Great Attractor as a final endpoint, astronomers began to see it as a gateway. It marks a location where local flows converge before continuing toward Shapley. The flows from Virgo, Hydra, Centaurus, and surrounding regions bend toward the Great Attractor because the gravitational influence is strong, but the flow lines then continue deeper into the region dominated by Shapley. The Great Attractor becomes a turning point in the gravitational landscape, a place where several filaments join before descending farther. Even when considering this larger structure, the area around Norma still plays a pivotal role. The cluster provides a gravitational centre of mass significant enough to anchor part of the basin, but its influence is enhanced by the surrounding filaments and by the mass in Hydra Centaurus. When all these contributions are combined, they create a broad basin rather than a sharp core. The elusive nature of the heart comes from the fact that this basin is not fully symmetrical. It is stretched towards Shapley. It is influenced by dark matter distributions that don't align perfectly with visible galaxies. It is partially obscured by the Milky Way, and it is shaped by filaments that feed into it from multiple directions. Another reason the heart remained difficult to define was that the internal structure of the basin changed the way galaxies moved. Instead of falling directly inward, galaxies approach from different angles, following pathways shaped by the underlying dark matter. Some approach along filaments from Hydra, others come from Virgo. Still others arrive from regions beyond Norma. These pathways don't converge neatly at a single point. They overlap in a broad zone, creating the appearance of a gravitational center, but without a singular structure to mark it. The heart becomes something defined by the pattern of motion, rather than by a discrete object. This is why the Great Attractor was first detected as a discrepancy in galaxy flows, rather than as a bright region of clustered galaxies. The gravitational influence was clear, even when the visible structure was not. The motions revealed the basin's presence long before telescopes uncovered the individual clusters that contributed to it. And even once these clusters were discovered, the mass distribution remained more diffuse and extended than expected. The Great Attractor's heart is elusive precisely because it is not a single heart. It is a system of related structures, woven together by gravity into a feature that influences motion across vast distances. When astronomers began constructing three-dimensional reconstructions of the gravitational field using peculiar velocities, they saw this complexity clearly. The region lacked a single perfect low point. Instead, it contained several dips, each associated with a cluster or filament. These dips merged to form the larger gravitational basin that shaped the motion of the Milky Way and surrounding galaxies. The deepest part of the basin leaned towards Shapley, while the local minimum close to us corresponded to the area around Norma. The heart of the Great Attractor sat somewhere in that blended zone, defined by the sum of mass rather than by a single structure. Further analysis revealed that the boundaries of the Great Attractor are not fixed. The gravitational landscape evolves as matter continues to move. Over billions of years, clusters merge. Filaments thicken. Voids expand. These changes shift the gravitational environment slightly, altering where the flow lines converge. This dynamism adds to the elusive nature of the region. Defining the heart of the Great Attractor is like defining the exact center of a river delta. The shape exists, the flow is real, but the center is spread across multiple channels. Even now, with advanced observatories, the exact contours of the region are still being refined. Upcoming infrared and radio surveys may reveal additional clusters hidden behind the densest parts of the zone of avoidance. Improved peculiar velocity measurements may refine the gravitational field further. But the overall understanding is clear. The Great Attractor's heart is not elusive because it is hidden alone. It is elusive because it is part of a larger, interconnected gravitational network. Its center is stretched, blended, and influenced by structures near and far. Its boundaries soften into the broader basin of Laniakea and extend toward the deeper pull of Shapley. When astronomers first realized that the flow of galaxies across our region of the universe didn't stop at the Great Attractor but continued past it, the conclusion was unavoidable. Something even more massive lay farther along the same general direction. The Great Attractor, once thought to be the strongest gravitational influence in the nearby universe, revealed itself to be only one part of a larger system. The motions of galaxies showed that the drift didn't simply slow down as they approached that region. Instead, the motion intensified beyond it. This meant the gravitational basin extended deeper than anyone had initially expected, and the structure responsible for that deeper pull soon became known as the Shapley Supercluster. The Shapley Supercluster is one of the most massive concentrations of galaxies in the observable universe. Early attempts to understand cosmic structure hinted at its existence, but it wasn't until flow studies and redshift surveys grew precise enough that astronomers could place it in its full context. Shapley lies farther from us than the Great Attractor, but its mass is so great that it influences the gravitational environment of entire regions closer to home. It contains dozens of major clusters, each filled with thousands of galaxies. The combined mass of these clusters produces a gravitational pull powerful enough to shape the motion of galaxies across vast stretches of Laniakea and beyond. The influence of Shapley was not immediately obvious because of the limitations in how surveys were originally conducted. Many early efforts focused on nearby galaxies or on regions where large optical telescopes could easily collect data. Because Shapley lies deep behind complicated areas of the sky, it received less attention in early mapping efforts. But as astronomers expanded their surveys and measured galaxy velocities across increasingly large volumes of space, they began noticing that the flow lines pointed well beyond the Great Attractor. In some cases, the lines bent sharply toward Shapley. In others, the magnitude of peculiar velocities increased with distance in a way that demanded additional gravitational influence from that region. Understanding why Shapley exerts such a strong pull required examining the mass of the supercluster in detail. Shapley is not a single cluster. It is a collection of clusters interconnected through filaments of galaxies and dark matter. These clusters merge into one another in a way that creates a continuous dense region of mass. Some clusters within Shapley are among the largest known. When astronomers measured the X-ray emissions from hot gas in its central clusters, the brightness of those emissions indicated enormous gravitational depths. These depths could only be produced by halos containing vast quantities of dark matter. The visible galaxies, impressive as they are, represent only a fraction of the total mass. The dark matter contributes most of the weight. This combination creates a gravitational force far stronger than anything in our immediate cosmic neighbourhood. The presence of Shapley also helped resolve inconsistencies in earlier attempts to model the gravitational field around the Great Attractor. When only local structures were considered, the peculiar velocities measured across our region were too large. But when Shapley was included in the calculations, the observed motions aligned more closely with predictions. This demonstrated that the gravitational environment was not dominated by a single major attractor, but by a hierarchy of structures, with Shapley at the top of that hierarchy. The Great Attractor sits on the slope of a deeper gravitational basin, and Shapley forms a major part of that basin's deepest region. This understanding also clarified why the motion of the Milky Way relative to the cosmic microwave background is as strong as it is. The speed is not simply a response to the mass in Hydra Centaurus Norma, or the immediate region of the Great Attractor. It reflects the combined pull of all the structures between us and Shapley, with Shapley itself acting as a dominant influence. Even though Shapley lies far beyond the Great Attractor, its gravitational field extends across immense distances. Gravity weakens with distance, but it does not disappear. When an object is massive enough, its influence remains significant even across hundreds of millions of light years. Shapley possesses enough mass to affect the motion of clusters near the Great Attractor, and by extension, galaxies closer to home. The discovery that Shapley plays such a large role also changed how astronomers understand superclusters in general. Rather than being simple, isolated structures, superclusters form part of even larger networks. They sit within webs of filaments that connect them to other massive regions. Shapley is part of such a network and interacts gravitationally with structures beyond its boundaries. The flow lines around it reveal that it is not the only massive region in that direction, although it is the most dominant. Clusters farther along the same filamentary structure contribute to the gravitational pull. The cosmic web does not end at Shapley. It extends farther, branching out into additional massive structures that continue shaping motion across even larger scales. This broader environment is essential for understanding the greater pull beyond Shapley. While Shapley is the largest and most influential structure in its area, the cosmic web does not place it in isolation. It connects to filaments filled with galaxies, gas, and dark matter. Some of these filaments extend toward clusters not included within Shapley itself. These external structures do not outweigh Shapley, but they support and reinforce its gravitational impact. The combined effect of the supercluster and its connected filaments creates a gravitational field large enough to influence the motion of galaxies across enormous distances. when astronomers simulated the motion of galaxies based on the mass distribution provided by visible galaxies and reconstructive models of dark matter, they found that including Shapley changed the dynamics dramatically. Without Shapley, the models underestimated peculiar velocities and failed to reproduce the observed drift of galaxies through Laniakea. When Shapley was added, the match improved significantly. The flow lines became consistent with observations, the gravitational basin deepened in the correct region, and the overall picture aligned with the actual motions of galaxies. This demonstrated that the greater pull affecting our region is not a mystery requiring exotic explanations. It arises naturally from the distribution of mass in the universe, dominated largely by dark matter. The presence of massive superclusters like Shapley shapes the flow of galaxies as part of this natural gravitational environment. The Great Attractor sits along the path of this greater pull, marking a region where the gravitational field created by Shapley begins to exert more influence. This makes the Great Attractor a transitional feature between local structures and the deeper gravitational descent toward Shapley. Understanding the relationship between Shapley and the Great Attractor required redefining what an attractor means in cosmology. An attractor is not necessarily a final destination where matter accumulates permanently. Instead, it marks a region where gravitational forces guide matter inward along specific paths. These regions can be nested within one another. A galaxy cluster may attract nearby galaxies. A larger supercluster may attract multiple clusters, and an even larger structure may attract entire superclusters. In this hierarchy, the Great Attractor draws local galaxies inward, but Shapley influences the motion of the Great Attractor itself. This layered arrangement means the pull felt at any point in the universe comes from a combination of structures at multiple scales. The discovery of the Shapley supercluster also reinforced the importance of voids in shaping cosmic motion. Voids are enormous empty regions with very little matter, including dark matter. Galaxies on the edges of voids experience uneven gravitational fields. They are pulled more strongly toward dense regions like Shapley and the Great Attractor, and less toward the empty space behind them. This imbalance enhances the flow. Voids do not pull, they allow matter to drift. This means that the presence of large voids surrounding the filaments, connected to Shapley, amplifies the gravitational influence of the supercluster. The Milky Way and surrounding galaxies sit near such regions, making the drift toward Shapley even more pronounced. Another important idea emerged as researchers examined how flows behaved across different distances. Galaxies closer to us show peculiar velocities pointing toward the Great Attractor, but galaxies farther away begin to show motion that aligns more strongly with Shapley. This shift indicates that the gravitational influence transitions from being dominated by the local basin to being dominated by the deeper basin farther along the same direction. This layered influence helps explain why earlier attempts to pinpoint the Great Attractor produced different results. The center of the local basin and the center of the larger basin do not coincide. They are offset, and the flow lines shift accordingly. This shift also shows that our region of space lies on a slope within the gravitational landscape. We are not at the bottom of a basin, we are somewhere along the side. The deeper the slope becomes, the stronger the pull. And that deeper slope continues towards Shapley. This means the motion of the Milky Way is not temporary. It is part of a long-term drift shaped by the cumulative gravitational field of the structures between us and Shapley. The motion will continue for billions of years as galaxies flow along the filaments of the cosmic web. What makes the Shapley supercluster particularly impressive is not just its mass, but its position within the broader cosmic structure. It lies along a major filament that acts like a gravitational highway. Galaxies flow along this filament, guided by the dark matter that forms its backbone. The structure of the filament channels matter towards Shapley, enhancing its gravitational influence. This is why the flow toward Shapley remains strong even across great distances. The structure doesn't disperse the flow, it organizes it. The discovery of Shapley's role also helped astronomers understand why the universe is not uniform on intermediate scales. While the large-scale universe appears homogeneous when averaged over enormous volumes, regions like Shapley demonstrate that significant variations exist. These variations create gravitational imbalances that shape motion. Such imbalances are natural outcomes of the early universe, where slight differences in density expanded into the large-scale structures we see today. Shapley grew from one of these slightly denser regions, accumulating matter through gravity over billions of years until it became one of the largest superclusters known. Even now, astronomers continue refining measurements of Shapley's mass. New surveys in infrared and radio wavelengths help identify more galaxies within the region. X-ray observations reveal hot gas in additional clusters. Weak gravitational lensing measurements map the distribution of dark matter. Each piece contributes to a more accurate understanding of the region's gravitational influence. But the broad picture has already been established. Shapley is massive enough to shape the motion of galaxies across enormous distances, including the motion of the Milky Way and surrounding clusters. As researchers continue exploring structures beyond Shapley, they have found indications of even larger formations farther out. These structures do not outweigh Shapley at the scales relevant to our region, but they hint that Shapley itself may lie on the slope of an even deeper gravitational basin. This does not diminish Shapley's role. Instead, it shows that cosmic structure is hierarchical at all scales. The flows continue, the patterns extend, the gravitational landscape becomes deeper and more complex with distance. When astronomers began mapping the motions of galaxies across the region we now call Laniakea, there was a moment when the data started to resemble something familiar, something almost geological in its shape. The way galaxies drifted inward along curved paths, the way their velocities changed gradually with distance, and the way the motion intensified toward a deeper region all resembled the movement of water flowing toward a low point in a landscape. It wasn't a perfect analogy, but the similarity was strong enough that many researchers began to think of the gravitational environment not in terms of isolated structures, but in terms of a basin. And once that perspective emerged, it changed how astronomers described the entire motion of our region of the universe. In simple terms, a gravitational basin is a region where the gravitational potential is deeper than surrounding areas. Anything not bound to a smaller structure tends to drift toward the basin's center. This doesn't mean galaxies move quickly. The distances are far too large for rapid motion. Instead, they drift slowly over billions of years, following the gentle pull of gravity along the filaments of the cosmic web. Their paths reveal the shape of the gravitational landscape beneath them, much like the path of water flowing along a slope reveals the contours of the land. The discovery of Laniakea relied heavily on these patterns. Galaxies across a vast region shared a common stream of motion, bending toward the same central zone. That convergence defined the boundaries of the supercluster, but the fact that galaxies converged toward the Great Attractor did not mean the Great Attractor was the deepest part of the basin. Instead, it marked a transitional region, a kind of intermediate slope within a larger gravitational valley. Further measurements show that the slope continued beyond it, leading deeper toward the Shapley supercluster. This extended slope indicated that our entire region of the universe sits inside a large-scale gravitational basin that continues much farther than originally believed. To understand what it means to fall into a cosmic basin, it helps to start with the peculiar velocities measured across the sky. These velocities represent the deviation from pure cosmic expansion. In a perfectly uniform universe, galaxies would drift apart in a smooth pattern, each receding from the others at a rate proportional to distance. But that uniformity doesn't exist on smaller scales. Regions of higher density pull matter inward. Regions of lower density allow matter to drift more freely. These variations create peculiar velocities, the subtle motions superimposed on cosmic expansion. By measuring these motions carefully, astronomers can infer the gravitational environment that shaped them. When these velocities are viewed in 3 dimensions, they reveal flow lines, paths that galaxies follow. These paths do not point in random directions. They curve gently toward areas of greater mass concentration. When many such paths are plotted, the result resembles a system of streams converging toward a central region. The motion of the Milky Way fits into this pattern. It moves toward the same region as many surrounding galaxies, indicating that it shares the same gravitational environment. The fact that our galaxy is not simply moving away from others uniformly, but drifting toward a specific direction, shows that gravity dominates our motion at the scales relevant to this basin. The Great Attractor serves as the closest gravitational low point within this environment, but it is not the deepest. It is part of the slope. The deeper region lies farther along near Shapley. This layered nature of the gravitational basin explains why the Great Attractor seemed so mysterious when first discovered. If astronomers expected a single object responsible for the motion, the complexity of the flow would appear confusing. But if the region is viewed as a sloped basin with multiple contributing clusters and superclusters, the motion becomes coherent. The galaxies are not being pulled toward a point, they're drifting down a gradient. Thinking of the gravitational environment as a basin also clarifies why flow lines converge but then continue beyond the Great Attractor. In a basin, the slope may include intermediate depressions, but the lowest point determines the final direction of the motion. Norma and Hydra Centaurus contribute to the intermediate region, making the Great Attractor appear prominent locally. But Shapley lies deeper on the slope, and the flow continues toward it. This is why galaxies beyond the Great Attractor show even stronger, peculiar velocities pointing farther along the same direction. They are falling deeper into the gravitational landscape. But falling into a gravitational basin doesn't mean galaxies are on a collision course with a single object. The expansion of the universe continues everywhere, including within the basin. Gravity slows that expansion locally, guiding motion, but it doesn't always reverse it. Superclusters like Laniakea are not gravitationally bound in the strictest sense. The expansion of space dominates on large scales. But within these vast regions, gravity creates patterns of motion that behave as though the galaxies were sliding into a valley on an ever-expanding surface. The galaxies move, but the surface beneath them stretches. This balance creates the unique combination of drift and expansion observed in large-scale flows. This idea can seem counterintuitive because falling suggests acceleration and eventual collision. But in cosmic terms, falling means drifting with the gravitational gradient, not racing downward. The galaxies remain separated by enormous distances, and the expansion of the universe continues to increase those distances. The gravitational basin creates a directional preference, not a physical collapse. Even if galaxies drift toward the deeper region for billions of years, the expansion of space keeps them far apart. The basin shapes the motion, but it does not pull galaxies into a single point the way gravity does at smaller scales. To grasp how subtle this motion is, one can consider the speed of the Milky Way relative to the cosmic microwave background. The velocity is significant on human terms, hundreds of kilometers per second, yet tiny in comparison to cosmic distances. At this speed, the Milky Way would take billions of years to traverse the distance to the deeper region of the basin. The scale is so large that even rapid speeds translate into slow progress. This is why the basin persists as a stable gravitational environment over cosmic timescales. The galaxies move slowly along the slope, but the gravitational relationships remain stable enough for the motion to reveal the underlying structure. Another important aspect of falling into a gravitational basin is the role of dark matter. Dark matter forms the scaffold of the cosmic web. It creates the potential wells into which galaxies drift. Without dark matter, the gravitational basin would not be deep enough to shape motions across such large scales. Visible galaxies provide only a small portion of the total mass. The majority comes from dark matter distributed across clusters, superclusters, and filaments. When astronomers reconstruct the gravitational field using peculiar velocities, the resulting map closely resembles predictions made by dark matter simulations. This consistency confirms that the basin is shaped by the invisible mass that dominates the universe. Filaments of dark matter also act as channels guiding the flow. Galaxies move along these filaments because that is where the gravitational potential is slightly lower. The filaments connect clusters into a continuous network. As galaxies drift along them, they participate in the overall flow toward deeper regions. The shape of the basin, therefore, is determined not only by clusters like Norma or massive regions like Shapley, but also by the arrangement of filaments and voids. Voids play a subtle but essential role by providing regions of weaker gravitational influence. They do not pull galaxies, but allow them to drift more strongly toward dense regions. The combination of filaments and voids creates the slope of the gravitational landscape. The Milky Way sits on one of these filaments. This filament connects our galaxy to Virgo. Virgo connects to Hydra and Centaurus. Those structures connect to Norma, and beyond Norma, additional filaments connect to Shapley. This arrangement creates a continuous pathway for motion, shaping our drift along the slope of the basin. The fact that this path exists shows that we are part of a much larger gravitational environment. Our motion is not isolated. It is influenced by the arrangement of mass across hundreds of millions of light years. Understanding that we are falling into a cosmic basin also changes how astronomers think about the future of our region. While galaxies drift along the slope, the expansion of the universe accelerates. On the largest scales, expansion dominates. But within the basin, gravity continues to shape motion in predictable ways. Over the next several billion years, galaxies within Laniakea will continue drifting along their flow lines. They will move closer to the deeper region of the basin, but the expansion of space will continue to increase the distances between them. The basin provides direction but not collapse. It defines motion but not eventual merging on supercluster scales. The basin also helps explain why the cosmic flow in this region appears coherent, even though individual clusters behave independently. Virgo, Hydra, Centaurus, and Norma all pull on nearby galaxies. But the deeper gravitational potential of the basin shapes the overall direction. Local structures add details to the motion, but the large-scale flow follows the slope created by the supercluster environment and the greater influence of Shapley. This hierarchy ensures that motions remain consistent over large areas. It also explains why galaxies within Laniakea share a common drift, even when they are separated by enormous distances. The idea of falling into a basin may raise a question about what lies beyond the basin itself. Shapley dominates the deeper part of the gravitational environment we experience, but it is not the only massive region in the universe. Large-scale surveys have identified structures even farther away. Some of these structures appear large enough to influence Shapley's motion. This does not diminish Shapley's role in shaping our region. It simply means that the cosmic web extends far beyond what we can observe directly, and that the gravitational landscape continues on larger scales. The basin we experience is part of a much larger network of basins and slopes, each shaped by the distribution of dark matter and galaxies across the universe. The question of whether the entire universe behaves like a collection of basins is a subject of ongoing research. On extremely large scales, the universe appears uniform, but on intermediate scales, it contains a hierarchy of gravitational environments. Each basin affects the motion of galaxies within it. Some basins merge, some overlap, some lie along filaments that lead to deeper ones. The cosmic web is not a set of isolated systems. It is a continuous structure shaped by the initial distribution of matter in the early universe. The flows we observe today are the result of that initial structure evolving under gravity for billions of years. From the perspective of our galaxy, falling into a cosmic basin means participating in a long-term motion shaped by the distribution of mass across vast distances. It means that our local motion is not random but part of a larger pattern. It means that the Great Attractor, Norma, Hydra Centaurus and Shapley are connected pieces of the same gravitational environment, and it means that the motion of the Milky Way is part of an ancient ongoing process that began long before our galaxy existed and will continue long after. When astronomers first noticed that the Milky Way and thousands of nearby galaxies were moving in a direction that couldn't be explained by visible structures alone, the discovery raised a question that went far beyond the search for one mysterious region in space. It forced scientists to reconsider how gravity operates on scales far larger than galaxy clusters and how the cosmic web responds to the distribution of mass across hundreds of millions of light years. The Great Attractor became more than a puzzle in observational astronomy. It became a test of our understanding of gravity itself and the patterns that arise when matter accumulates on cosmic scales. The first hints that something larger was at work came from the peculiar velocities measured across the local universe. These velocities were not small. They were not random. They were not symmetrical. They pointed in a consistent direction, suggesting the presence of a gravitational feature that influenced motion across a vast region of space. This was important because gravity weakens with distance. For a structure to affect the motion of galaxies as far apart as ours and those in distant clusters, it would have to be enormous. Traditional models of galaxies and clusters didn't provide a way to explain such an influence unless something larger existed. This meant that the Great Attractor was not just a new detail in the cosmic map. It was an indicator of how gravity shapes structure far beyond the scale of individual clusters. As astronomers looked deeper, they found that the gravitational influence couldn't be traced to a single object. Instead, it spread across a region filled with multiple clusters, filaments, and dark matter concentrations. This complexity revealed something essential about gravity on large scales. Gravity doesn't create simple spherical structures in the universe. It creates networks. It forms filaments of dark matter that stretch across cosmic distances. It draws galaxies along those filaments, and instead of forming a single central mass, it forms many smaller concentrations connected to one another. The Great Attractor demonstrated this clearly by refusing to behave like a standalone object. Its influence came from the entire arrangement of matter around it. This arrangement revealed the first major insight. Gravity is not only powerful at pulling matter together, it is also sensitive to the distribution of mass. If matter were evenly spread across the universe, peculiar velocities would be small or non-existent. But because matter is unevenly distributed, gravity creates deep basins where matter accumulates and wide voids where expansion dominates. The Great Attractor sits in one of these basins. The fact that galaxies move toward it shows how gravity responds to unevenness in the distribution of matter. Even a small imbalance in density on large scales becomes magnified over billions of years. The slight differences grow into enormous structures, and the motion of galaxies becomes a record of this process. The next insight comes from how the Great Attractor fits into the broader cosmic web. The gravitational basin it forms is not isolated. It lies on a slope that leads toward the Shapley Supercluster. This hierarchical arrangement demonstrated that gravity shapes structure in multiple layers. A cluster like Virgo affects the motion of nearby galaxies. A larger region like the Great Attractor affects the motion of clusters, and an even larger region like Shapley affects the motion of supercluster scale structures. Gravity works at every layer, and the flow of matter reflects this hierarchy. The Great Attractor provided the clearest observational evidence of this layered gravitational influence. Before astronomers mapped out Laniakea, the idea of defining superclusters by gravitational flows instead of by galaxy counts had not fully taken hold. The Great Attractor changed that. It showed that structure cannot be understood by looking at galaxies alone. It must be understood by studying motion. Galaxies reveal where matter is. Motion reveals how matter is arranged. When the flow lines were traced, they revealed a coherent pattern that defined the boundaries of Laniakea. This showed that superclusters are not static clusters of galaxies. They are regions where gravity guides the flow of matter. The Great Attractor played a central role in revealing that. It marked the region where many flows met before continuing towards Shapley. It defined the turning point in the gravitational landscape. Without it, the structure of Laniakea might have remained hidden. Another key insight from the Great Attractor came from the realization that dark matter must dominate the gravitational field in this region. Visible matter alone could not explain the strength of the drift. The galaxies and clusters we can see provide only a small fraction of the mass needed. The remainder comes from dark matter. This reinforced the idea that dark matter is essential in shaping cosmic structure. It is not an optional ingredient. It is the main component that determines where galaxies form, how filaments connect, and how basins develop. The Great Attractor provided a natural test of this idea. The gravitational influence matched models only when dark matter was included. Without it, the numbers didn't work. The observed velocities would have been impossible. These observations strengthened the case for dark matter halos around clusters stretching far beyond the visible galaxies. They showed that large-scale gravitational features like the Great Attractor are dominated by dark matter. And because dark matter interacts only through gravity, it accumulates in regions that gradually deepen into gravitational basins. The Great Attractor's elusive nature, its extended shape, and its dependence on multiple clusters all pointed to dark matter as the backbone of the structure. Without dark matter, the gravitational environment would be shallow, the flow of galaxies would be weaker, the structure of Laniakea wouldn't form as it does. The way the Great Attractor interacts with the Shapley supercluster also provides insight into gravity on even larger scales. The flows toward Shapley are stronger than the flows toward the Great Attractor. This means Shapley creates a deeper gravitational basin. The fact that the Great Attractor sits on the slope of that basin demonstrated how gravity influences structures that are themselves gravitational features. The Great Attractor is not simply pulling galaxies inward. It is being pulled inward itself. This cascading influence provides a rare glimpse into how gravity organizes matter across supercluster scales. It shows that gravity has no upper limit on how large a structure can be shaped by its influence. It also shows that the universe is structured in a nested way, with smaller gravitational features embedded inside larger ones. This insight led astronomers to rethink earlier models of cosmic structure. Instead of imagining the universe as a series of disconnected clusters, they began to see it as a connected web where each part influences other parts through gravitational relationships. The Great Attractor helped reveal these connections. It provided the key transitional region between local structures and more massive regions farther out. Without it, the link between local flows and large-scale flows might have remained unclear. Another breakthrough came from understanding how voids shape the gravitational environment. Voids are enormous regions with far less matter than average. They do not pull galaxies. But because they lack mass, they allow galaxies to be pulled more strongly toward dense regions. This means that voids amplify the gravitational influence of structures like the Great Attractor. When galaxies lie between a void and a dense cluster, they experience a one-sided gravitational environment. The Great Attractor draws material inward not only because it is massive, but also because the regions behind it contain less matter. The shape of the gravitational basin depends not only on where matter is, but also on where matter isn't. This asymmetry strengthens the pull and makes the flows more pronounced. The Great Attractor also revealed something important about gravitational maps created from motion rather than from light. When astronomers traced peculiar velocities, they effectively created a map of the gravitational potential. This map didn't show clusters, it showed gradients, it showed slopes, it showed basins. These patterns matched predictions from models of cosmic evolution. The agreement confirmed that gravity behaves consistently across scales, and that peculiar velocities reflect real gravitational structures. This was crucial because it validated the technique of using motion to infer mass distribution. Without this validation, the concept of Laniakea might not have taken shape with the same clarity. These insights helped refine cosmological models. They provided real-world tests for simulations that model the growth of structure in the universe. When researchers compared observations of the Great Attractor region with simulations, the match was striking. The simulations naturally formed features similar to the Great Attractor when dark matter was included. They formed filaments, clusters, and basins that resembled the observed structures. This agreement strengthened confidence in the standard model of cosmology. It showed that the large-scale structure of the universe is not random. It follows patterns shaped by gravity acting over billions of years. The Great Attractor offered an observational anchor for those patterns. It also highlighted the importance of scale. Gravity behaves identically on all scales, but the results vary depending on how much matter is involved. On small scales, gravity binds stars into galaxies. On larger scales, it binds galaxies into clusters. On even larger scales, it shapes the motion of clusters into flows. The Great Attractor revealed the next step in this sequence. It showed how gravity operates not on millions of light years, but on hundreds of millions. It showed how large-scale mass distributions create gravitational environments that dwarf anything within galaxy clusters. It provided the clearest example of how supercluster-scale gravity works. Another insight came from the realization that the Great Attractor is not a static object. The gravitational environment evolves over time as matter flows along filaments. Clusters merge, voids expand. The location of the deepest part of the basin may shift slightly over billions of years. This dynamism showed that the universe is not a fixed structure. It is constantly reshaping itself under gravity's influence. The Great Attractor is just one moment in that process. It formed gradually as matter accumulated. It will continue to evolve as galaxies move along the gravitational slope. This perspective helps scientists understand that cosmic structure is not permanent. It is a snapshot in a longer sequence of changes. Despite this evolution, the gravitational patterns remain stable enough for galaxies to follow them. The basin deepens slowly. The flows adjust gradually. The overall shape of the gravitational landscape persists across cosmic time. This stability allows astronomers to use the Great Attractor as a reference point. It also helps them understand how other regions of the universe may contain similar basins, each influencing the motion of galaxies within them. The patterns observed near the Great Attractor likely repeat elsewhere in the universe, forming a network of gravitational basins connected by filaments. These revelations also help researchers explore whether gravity behaves differently on the larger scales. Some theories propose modifications to gravity to explain cosmic acceleration, or the behavior of dark matter. The Great Attractor provides a large-scale laboratory for testing these ideas. So far, the gravitational field inferred from peculiar velocities matches predictions from general relativity and dark matter models. This consistency strengthens the case that gravity behaves as expected, even on supercluster scales. But the region also serves as a reminder that large-scale tests are essential. Without mapping flows, astronomers would not know whether theories match reality. The Great Attractor became one of the first regions where large-scale gravity could be tested with precision. As astronomers pieced together the full picture of the Great Attractor, the Shapley Supercluster, the vast filaments connecting them, and the immense flows guiding galaxies across hundreds of millions of light years, a different understanding of our place in the universe began to emerge. It wasn't centered on an object, a cluster, or even a single region. It grew from the realization that we live inside a network of gentle, persistent motions, shaped by the distribution of matter on scales so large that even our imaginations strain to hold them. These motions don't resemble the chaotic turbulence of storms or the violent collapse of cosmic collisions. They unfold quietly, steadily, with a kind of subtle order that reflects the slow work of gravity acting over billions of years. Looking at them feels a little like watching a tide that never stops rising and never fully retreats. A movement too slow to feel in any ordinary sense, but unmistakable when the data are mapped and compared across time. The idea that the Milky Way drifts along these vast currents comes from the peculiar velocities measured across our region. These velocities, though modest compared to the expanses they cross, reveal the influence of the gravitational landscape that surrounds us. They show that our galaxy is not drifting aimlessly. It moves with countless other galaxies along paths shaped by deeper gravitational basins. The slope that begins near Virgo, descends through Hydra and Centaurus, bends inward near Norma, and continues towards Shapley defines a long-term motion that traces the structure of the universe at its grandest scale. This motion is not directed by any single event or explosion. It's not forced by an external push. It's simply the natural response of matter to the shape of the gravitational terrain beneath it. The gentle drift of galaxies can feel distant when described in technical terms, but the idea becomes more relatable when imagined as part of a larger ongoing flow. Galaxies move along filaments like leaves caught in slow currents. They drift toward regions of greater density, influenced not by sudden forces but by the quiet pull of gravity acting over unimaginable lengths of time. Our place in this motion is neither privileged nor isolated. It's typical of countless galaxies scattered across the cosmic web. Yet the typical nature of the motion doesn't make it any less remarkable. It means that the universe itself is arranged in such a way that structure leads to movement. Movement leads to flows, and flows create boundaries that define entire superclusters. Understanding that we drift through these vast currents also changes how we think about stability. On human scales, stability is measured in predictable cycles and consistent surroundings. On cosmic scales, stability is measured by slow change. The cosmic web doesn't shift abruptly. The gravitational basin of Laniakea doesn't transform overnight. The galaxies follow their gentle gradients across tens of millions of years. The motions are so slow that no single generation will ever observe a noticeable shift. Yet the long-term trend continues without interruption, and the flows remain consistent enough that astronomers can map them, compare them, and outline the shape of the gravitational landscape that directs them. This slow drift places the Milky Way in a very particular position. We sit on the edge of a vast supercluster, far from its densest cores and close to the boundaries where flow lines separate into different directions. This means that our galaxy is part of Laniakea but not deeply embedded within its central region. Our motion reflects the influence of the basin, but not with the intensity seen closer to Norma or the deeper regions leading towards Shapley. The Milky Way's path still follows the gravitational slope, but the pull it feels is more of a subtle guidance than a strong descent. This position gives astronomers a good vantage point for studying flows across a large area. From here, peculiar velocities reveal the overlapping influences of nearby clusters and more distant superclusters, all contributing to the shape of the drift. Even though we drift along this slope, the distances involved are so immense that the motion does not threaten to collapse structures into one another. The expansion of the universe still dominates at the grandest scales. Galaxies separate as space expands, even as gravity guides their paths. This interplay of expansion and gravitational flow creates a kind of cosmic balance. Galaxies move inward toward denser regions, but the space between them stretches. The motion is real, but the collapse is prevented. The expansion continues, and the basin remains a pattern of direction rather than a final destination. Understanding this balance helps make sense of the structure of the universe. It means that even as galaxies drift into gravitational basins, the universe as a whole remains dynamic. Structures grow slowly. Filaments lengthen, voids widen, clusters merge occasionally. But the overall shape persists for billions of years because gravity works against expansion without overwhelming it. The flows reveal where gravity's influence is strongest, but do not suggest that the universe is collapsing into a single point. Instead, they show that the universe's structure is self-organizing, with matter responding to gravity in a way that creates coherence without erasing separation. The particular flow we experience today began long before the Milky Way existed in its current form. The dark matter halo that would one day hold our galaxy together was already drifting along the gravitational slope billions of years before the first stars formed. Those early motions shaped the position of the halo relative to larger structures. As gas accumulated, cooled, and eventually formed stars, the halo continued drifting, carrying the early Milky Way along the gravitational terrain. Even as the galaxy built its spiral arms, formed clusters, and produced generations of stars, the motion through the basin continued. The drift is older than the galaxy itself. It will continue long after the Milky Way merges with Andromeda and transforms into a new system altogether. This continuity creates a sense of perspective about time. Human lifetimes are brief compared to even the smallest cosmic cycles. The solar system's journey around the Milky Way takes hundreds of millions of years. The galaxy's motion through Laniakea spans billions. The flow toward Shapley, if measured from deep cosmic history to far cosmic future, covers stretches of time that make every astronomical event of human interest feel fleeting. Yet the slowness of the drift doesn't diminish its significance. It highlights the long-term stability of the universe's structure. When motion continues for billions of years and remains consistent enough to map, it means the forces shaping it are steady and reliable across almost unimaginable spans of time. This reliability offers insight into why the universe looks the way it does. If gravity were chaotic or unstable on large scales, the cosmic web would not exist in its current form. Instead, the consistent behavior of gravity allows small initial differences in density to grow into clusters, superclusters, and filaments. The flows that converge near the Great Attractor and continue toward Shapley reflect this growth. They show that the universe, despite its complexity, follows predictable rules. The structures we see are not accidents. They are the natural outcome of gravity acting on matter over time. One of the quieter realizations that emerges from studying these flows is that the universe has patterns that repeat across scales. Clusters attract nearby galaxies. Superclusters attract clusters. Filaments guide motion across even larger distances. And beyond the scales we can observe directly, even larger structures likely influence the motion of superclusters like Shapley. Each level reveals a pattern similar to the level below it. The universe appears to be built from these nested relationships. Wherever matter is unevenly distributed, gravity responds by shaping it into a structure that influences motion, and wherever flows converge, gravitational basins form. These patterns appear consistently across the observable universe, forming a kind of quiet geometry that reveals itself only when viewed through motion. The notion that we move through gentle cosmic currents also adds a kind of grounding perspective about how we observe the universe. When telescopes point outward, they capture light that has travelled across vast distances, but they also capture information about the motion of the sources of that light. Every redshift measurement, every peculiar velocity calculation, every map of filamentary structure reveals not only where galaxies are but how they are moving. When these motions align over large areas, they reveal something deeper, the shared gravitational environment that shapes them. Observing these motions is like watching leaves on a calm river. Their paths reveal the underlying flow. The galaxies reveal the gravitational currents beneath the expanding fabric of the cosmos. The long drift also raises a question about how we situate ourselves within this environment. When we think about our position in the universe, it's easy to imagine the Milky Way as a fixed location, anchored to a particular spot in space. But the reality is more dynamic. The galaxy rotates around its centre. The solar system moves within one of its spiral arms. The Milky Way drifts toward Andromeda. And the entire local group moves through Laniakea. This layering of motion means that our position is never static. Every scale reveals a new movement, and each movement reflects the gravitational relationships at that scale. This doesn't create instability, it creates continuity. The motions are regular enough that astronomers can calculate them precisely. The drift toward the Great Attractor is not surprising once the full mass distribution is understood. The continuation of the flow toward Shapley aligns perfectly with predictions based on dark matter and the cosmic web. The coherence of these motions shows that the universe is not random, it is structured, and that structure guides everything within it. The quiet motion of the Milky Way through this structure can be seen as a kind of cosmic inheritance. We move the way we do because of how matter was arranged billions of years ago. The dark matter filaments that shape our path formed early in cosmic history, long before galaxies assembled. They determined the gravitational environment long before stars were born. The flow we experience today reflects that history. It is the long-term consequence of the universe's earliest moments. Understanding all of this gives the drift a sense of continuity rather than finality. The motion we observe today will continue, but it won't reach an abrupt endpoint. The gravitational basin will persist, even as expansion carries galaxies farther from one another on the grandest scales. The currents of motion will remain gentle and steady, a background pattern beneath everything else that happens. The structures may evolve, but the overall shape of the gravitational environment remains coherent enough to guide matter for billions of years. As we reach the end of this long journey through clusters, superclusters, dark matter, filaments, voids, flows, and gravitational basins, the picture that remains is not one of mystery or uncertainty, but of a quiet, persistent order. The Great Attractor may not be a single object. Shapley may not be the final destination of any motion. Laniakea may not be a bound structure in the traditional sense, but each of these features reveals the same underlying truth about the universe. Gravity shapes matter into patterns that last across cosmic time. Those patterns guide motion across unimaginable distances, and our galaxy drifts peacefully within one of those vast currents, carried gently along the gravitational landscape that the universe built long before we arrived to observe it.